the trajectory is to be first is sorry. Hold on. It's very noisy. Who have to mute this one? Okay, it's very noisy. Okay, I have to mute. It's very noisy. Sorry, I have to mute your microphone. Otherwise, we cannot continue. All right, and then we go to. Okay, this. The first, if the free fly trajectory is to be circular, second parabolic, third one is elliptical, and last one is hyperbolic. In this four case, what is height from satellite to the surface of the Earth in order to make this flight? One is circular, make circular, this one circular. Second is parabolic, this parabolic, this one, E equal to 1. Circular E equal to 0. And the ellipse, this one, is E less than 1. Okay? And the D is a hyperbolic, which is E larger than 1 for this trace. Ask you, for this trace, what is the initial height from satellite to surface of the Earth? This question. Okay, how can we solve that? Okay, we look the solution. So first of all, we understand this is your Earth, that the R0 is from center of Earth to the satellite, this distance. We really want to find out this height from this satellite to surface of the Earth. So that this height should be equal to R0 minus the radius of Earth. That's we should clear, okay? For the circular trajectory, okay? And then this E equal to 0. So again, we go to the equation 13 to 18 or 12 to 20 or 13 to 21. I think 13, not 12, sorry. 32 to 1 in this page, which is this download. This your I believe this is your textbook. Textbook is download here. You can download. I already have self. Okay, download. Yeah, this download. Open up. Which page? Just again. That's your textbook. Textbook. Which page? He's said at the page. Page 158. Page 158. So you reach the 158 page. 57, 58, I think is here. 57, 58, okay? So 58, you can find an E definition, E, this is your E, okay? And it's your E, find the E, okay? E is this one, from this one. 113.21, for this is your E, right? This is C, okay? This is C, and E is what? E is this one. Put the C inside here. So C is this one. And E is this one. Put C, put it here. You get your E equation. Which E equation is equal to this one minus 1. Okay, this is your E equation. And then for the we know for this circular trajectory is E equal to 0. So we go to E equal to 0. And then you from here you solve the V0. In this way, solve the R0. You can find where is R0. Whereas G is gravity constants, okay? And then ME is mass of Earth. V0 is the initial velocity, and you can calculate this R0. And this R0 is from here to here. So you have to minus this Earth's radius, you get the H. So H should be equal to this R0 minus the radius of Earth equal to 316,633 kilometer, and that's the height, altitude. Okay, this is for first question. If the second is circular. The second one, if this fly flight trajectory, if this trajectory is parabolic, and then according to this definition, parabolic deflation, if it's a parabolic, which is parabolic E equal to 1, see that? Parabolic equal to 1. Then you go to use the E, this formula, equal to 1. Equal to 1, which means this one equal to 1. And they solve this from here, solved what is R0. The R0 should be equal to this one. This is the gravity constants. And this is the mass of Earth. And put this mass of Earth here, this constants, gravity constants here, and then divided by initial velocity. What is initial velocity? We will give initial velocity calculate here. Initial velocity 4,000 kilometers per hour. You change into SI units. Kilometer become 1,000. Hour divided by 3,600, and this one give the V0 is 1,000. Sorry, this is 11,000. This is 1,111.11 meter per second. Okay, so that's called V0. For this V0, you put the V0 put here. This is V0, and this is G is the constant of gravity constants, and ME is the mass of the Earth. Okay, you calculate R0 this one. So this one, and then we know the radius of the Earth is 6,378. So use this R0 minus the radius of the Earth equal to the height. So from here, so you get this is your R0 minus radius of Earth. Then you get this is your height. So that's why I get for the parabolic free flight trajectory, and equal to this is your R0 minus the radius of the Earth equal to 339,644 kilometer height. Okay, then we go to this for parabolic. Then we keep continue, and if for the elliptical free flight trajectory, and the E should be less than 1, larger than 0, because according to this graphic, elliptical E equal less than 1, larger than 0. This is your elliptical. If not larger than 0, equal to 0 becomes circle. It's larger than 0 between circle and the parabolic become elliptical. So that E should be less than 1, larger than 0. So how can we solve this one? We know the E is this one less than 1, and you solve this one less than 2, and you calculate R0 less than this one, and R0 and then minus radius of Earth both sides, and this is your H. You calculate that one. So if the E less than 1, you have a guarantee H should be less than this amount. Okay, this 639,644 kilometer height. And then if E larger than 0, E larger than 0, this is E larger than 0, and then you should make sure R0 larger than this one. And you calculate R0 larger than this one minus both sides are RE, the radius of Earth, and you get H. Okay, and this is 6,378 radius of Earth. And then use this one we calculate before. This is we can calculate this one is this you make a calculation is 323,011 minus this radius of Earth equal this is your height. Okay, so when E larger than 0, you have to make sure H should be larger than this one. So the E equal to less than 1, larger than 0, H should be less than this one and larger than this one. That's your answer for the if free flight trajectory, if it's parabolic, and they should be in this range for the height of satellites. And if you for the hyperbolic free flight trajectory, and then if like that, and E have to larger than 1. Why? Because this is from here, this graphic, hyperbolic trajectory, E larger than 1. So you use the E definition. Okay, E is this one definition, larger than 1. Then move to right hand side. So this one R should be larger than this one. You put all these gravity constants, Earth of mass of Earth, and also initial velocity inside, can calculate minus the radius Earth. And then you get this one, get this result, this one, get this result, minus this radius of Earth equal to, and this result, 339,644. So in this case, if your if it's for satellites moving in the hyperbolic free flight trajectory, E larger than 1, you have to certify H larger than 339,644 kilometer. Okay, that's the result. So we finish all the results. Very important, you find what definition of E. And then for each of the chase, each of free flight trajectory, and what is E range? You have to, from this graphic, find the E range. So E is equal to 0, E larger than 0, less than 1 for the elliptic, or is if E is equal to 1, which is parabolic, or larger than 1, hyperbolic, according to E range, and also E definition, you can find R0. R0 minus radius of Earth, you get height. That's how you solve this issue. Okay, for solve this issue. Okay, clear? Any question for this one? Do you understand? We may talk a little bit more at end of this lecture. We teach a little bit more about this free for the motion of free forced motion. Okay, it's called, hold on, it's called central force motion and space mechanics. End of this, before we finish today's workshop, we have talk a little bit more. So this is only an example. Okay. So do you have any further question regarding problem 5? Any question? Am I clear? Any other questions? If not, we have to move. Okay. Then we finish this week 3 questions. Okay. Then we close this one. And then we close the week 3. This question, we already fully solved these questions. Then we go to week 4. Okay, week 4 question, because we don't have time, the workshop 1. Okay, week 4 question, we read this question. Question 1 is when the driver applied the brake of a light truck travel 40 kilometers per hour, and you have used this one, convert the SI units, 1,000 divided by 3,600. Okay, and then it skips 3 meters before stop. Then the stop distance. Stop distance, what formula you should use? Deceleration. You should use this formula. Okay, this end of a speed equals 0. Initial speed U square, and this should be minus because of deceleration. And here stop distance should be U square divided by 2A. Stop distance. You use this formula. Okay, so then how far? From here, these two, you know the speed, you know the stop distance, then you can easily find what deceleration. Okay, and keep the same deceleration. If the initial speed is 80 km per hour, you have a initial speed 80, and you have acceleration, and the calculate and another stop distance. So how far will be the truck will skip before the stop? If and when the brake is applied, maintain the same acceleration, how far this truck skip, okay, before the stop? Which you use the same formula. You use this same formula, then you change it, and new is 80 km per hour, not 30. Okay, this is equal to 0. So 80 is here, 80, and this is acceleration same from last step. Okay, and then calculate the new what is S, stop distance. So that's the how we solve this issue. So we go back how we solution, how to do that. So first of all, use this formula I mentioned before. Use formula is this formula, and this is and the brake is 0. Only have initial velocity, and this minus. From this one, you can calculate stop distance is U square divided by 2A. This one, U square V square divided by 2A. This is your stop distance. Okay. Now we know initial speed is 40 SI units, 1,000 divided by 3,600. We know the stop distance is 3, right? And then we should be able to calculate the acceleration. So you here swap the position S and A. A put here, S put here, and formula become here. So you know initial speed is 40 kilometer per hour. Kilometer is 1,000 per hour, 3,000 600 becomes second. This one, after you multiply, it becomes meter per second. Okay, and this is v squared divided by the stop distance 3, and use this formula. You can calculate this is acceleration is 20.576 meter per second square. Okay, we can check it again if you write on the line. So equal to first we check this formula is okay, is 40 multiply 1000 divided by 3600, and that is square. Okay, divided by 2 first, and divided by another 3. Divided by 2, divided by 3. Or if you don't want the 2 divide, you can divide the bracket 2 multiply 3. The same thing. You can get the same result. You get same result. And that's your acceleration. Okay. And if you know the acceleration, then you use the same formula. You know, as now speed is 80 kilometers per hour. You know, keep the same acceleration. What is stop distance? Use this formula. So this formula, it should be equal to is 80. Now it's 80 multiply 1000 and divided by 3600. Okay, you change the kilometer per hour become SI unit meter per second, and this is your velocity, and the velocity is square, and velocity square divided by 2 first. This will first divide by 2. Or if you want to, you don't want to divide 2 times, you can use brackets 2 times. And this 20.5, use this one, okay, and then enter, and then they should give you the results. It is 12 meter. So this stop distance will be 12 meter. So straight away, and then you check your results. It will be 12 meter straight away. Okay, then we go move to another question. The ski start from position A, okay, travel down to the ramp. We know this one. This have a gravity potential energy, MGH, and convert to the kinetic energy, because this one originally have no speed and now have a speed. So this potential energy of gravity change into the kinetic energy, half of mv squared. So it's the first formula. So after you get this velocity, and then from here jump to here. So if friction and air resistance, okay, is ignored, okay, and this skip A will be start from 0 and travel down the ramp, okay, and then when he reached B, okay, also find the distance S when he striked on the ground C. If he make jump, travel horizontal at the B. Horizontal at the B, okay, you get speed now horizontal at B. This speed direction is like that. Okay, just ignore the skid size, and he has a mass of 70 kilogram. Okay, and from here, after he reached here, then he have 2 direction. One horizontal direction. They don't have the force in horizontal. That's horizontal should be constant speed. So we from here, from this jump MGH equal to half of mv squared. He should find the velocity. The velocity times t should be equal to this s cosine 30 degree. That's horizontal is constant speed. For the vertical, this free drop, okay, because vertical, this free drop, they have an acceleration will be g 9.8. Okay, the whole distance will be 4, and multiply this height. This height is how much? S sine theta. S sine theta plus 4. This is the distance you're going to drop, and this distance drop should be equal to half of gt square. Okay, from gt square. Okay, that is the vertical, and this t should be same as the t horizontal travel, which is v times t should be equal to s cosine theta. That's how we can solve this problem. So we go back to the solution. So equation 1, you can see that you have a gravity potential energy from here to here. You have a height, 50 meter height, mgh. This potential energy, gravity should be transfer to the kinetic energy, half of mv squared. So to get the first formula, and you cancel the m, you can calculate this v squared 2gh, and 9.8, and this is height is 46. Why is 46? Because you see that, because we stopped here. See that a jumped to here. So here to here is 4. So 50 minus 4 is from here to here. This is a distance. So 46. And because he dropped B, not dropped here, dropped B. So that's why 50 minus 4 equal to 46. And then from here you can calculate. You get the 30.02665. And this speed, you convert your the gravity potential energy into the kinetic energy, half of mv squared. You calculate v. V is 30 meters per second. Okay, and then you get vt for horizontal vt. Okay, vt is travel horizontal distance. Okay, horizontal distance is horizontal distance is this distance. This distance equal to, because this divided by this equal to tangent is, because this is 30 degree. So this one and divided by this one, tangent is 30 degree. Okay, so then you use this one, and this one tangent is 30 degree, they equal to this one, and plus 4. Okay, that's your vertical, your travel distance. Horizontal, so that's you see that vt tangent is that. Vt tangent 30 degree is this one. So vt is this distance. Okay, vt is this distance. Tangent 30 is this one. And plus 4 is the total drop distance in the B from here to here. Okay, so that's you get the vt tangent 30 degree plus 4. That's your vertical drop distance. Should be equal to this travel s. Then this one go to another formula, which is acceleration, which is go to this one formula. So your initial will be 0, and in the vertical 0 h equal to half of gt squared. This formula, and then you go to that, and this is your total h equal to half of gt squared. And from here you get the t squared and t, and put this v is speed is 30, all right, and the tangent is 30. They should have number there. And then you organize this equation, it becomes the t squared t, and then this a, this b, and this c. And to solve this equation, we learned before, this 2a minus b plus minus square roots, and b squared minus 4ac. We learned this formula before. Solve this equation from the middle school, high school, right? So you calculate this one equal to t. T should be equal to, make a calculation, t should be equal to 3.755 seconds. Okay, solve calculation this formula. And if you're interested, I can show you how to calculate. No problem. And we can equal to the numeric should be 3.30.02665. Okay, multiply tangent. Okay, 30 degree. Be careful, you have to make a radial. Pi divided by 180. Always change the degree to the radial. Okay, and then plus y is not minus, because this one, if it's minus, this one is larger than this one. Minus become negative. You won't get the negative time, right? So that's why it's plus. No, the formula have plus minus. You take the plus. If minus, you get the negative time. That's not possible. Okay, so then plus the square roots. And inside will be so inside will be 30.02665 multiply tangent, again the same thing at 30 degree. Okay, and multiply pi and divide by 180. Okay. That's and divide by 180. This is for the tangent, and also you have to bracket again, and then the square. Okay, and the plus for the Excel is very very good tool, but be very careful to miss the brackets. Be very careful. You have to be very careful. Otherwise, you can use the calculator. The calculator is boring, take a long time. A multiply 9.8. Okay, and the brackets again. After get brackets, and then you get another bracket. First bracket is for the square root. Another bracket is for the numeric, and the divide by 9.8. And this one should be give you result 3.755, and that's your results. Okay, so you get the time is 3.755, and then this is your vertical direction. We finish vertical direction, which is we from here, and this 4 plus this drop distance, which is this VT tangent 30 degree. This you finish it. So this direction distance equal to half of GT, and you find the T equal to that. And then we study horizontal. Horizontal VT is equal to here, horizontal VT, this velocity VT is this one, equal to S cosine 30 degree. So equal to S cosine 30 degree. And from here, you can calculate S, because V, 30.02. T, T is 3.755. And then you divide by cosine 30 degree. And this one, how much we can calculate for you? This one should be equal to 30.02665, right? And multiply and 3.7. You can if you can sometimes you can, you're lazy, you can use this one, save your time. You can select that one, multiply that one. That's good enough. And divide by cosine. Okay? Cosine, and this is 30 degree. And multiply, change the degree to the radian. Pi, be careful, it's not pi only, have brackets, okay? And divide by 180. This is your calculated formula, and then you enter, it's 130.2, and that's your results. So what is the answer? 130. Okay, 0.2, he just ignore. That's the problem. Okay, then we move to the question 3. Question 3 is that the roller coaster and its passenger both have a total mass m, and determine the smallest velocity it must have when it enter from here, enter this loop at A position, so that it can complete the loop, not leaving the track. Which means in this position, the gravity, the weight, gravity force should be equal to centrifugal force. The balance, they will not drop. If this weight larger than the centrifugal force, this one will drop. Otherwise, at least maintain the mg should equal to centrifugal force, and then can make full run. Okay, so will not leave the track. Also determine the normal force of the track exists on the car when come along to the bottom point at C. Okay, the radius of the curvature of the track at B is low B. Low B is here, and at C is low C. Okay, just ignore the size of the car how to solve this problem. And at the beginning, this car ends into A point. You have the velocity, of course. Then they only have a kinematic energy. Okay, they have a kinematic energy, which is half of m or v square, right? Half of m v square. This kinetic energy, and this kinetic energy will be moved up until here, become the gravity potential energy, mgh. Okay, plus this car still have tangential velocity, which is m half of m v square. So we write this equation first. So we go to, at the beginning, kinetic energy, and they have to convert into here, have a gravity potential energy, mgh. And because this car have tangential velocity, and another kinetic energy. That's the energy balance conservation from this point to this point, energy conservation. At this point, we know that at this point, the weights should be equal to centrifugal force. Otherwise, they will drop off. And mg should be equal to mv squared divided by r. At cancel of m, then you get the g equal to vb squared divided by r. So vb squared should be equal to g multiplied the rho b. That's for sure. And here we can cancel the half m. We cancel m, cancel m, cancel m. And also multiply the 2 at the same time. Then you can get a VA equal to 2 GH. Cancel the half and cancel the m. Okay, rho equal to VB squared. But the VB squared equal to rho BG. So it becomes rho BG. Okay, and the VA square roots. Okay. And the same scenario, if we study this point, C point also have a VC square kinetic energy should be equal to this point. This point should be potential energy of the gravity and kinetic energy of these speeds, tangential speeds, kinetic energy. So only this become VC. So use same formula and also meet the same criteria. So VA should be equal to VC. In this case, VA should be equal to VC, right? Because you get same formula. This VA change to VC. Get same formula. So VA here should VA equal to VC. I should write down that. Oh, sorry, because otherwise you have to understand. Okay, we open this one up. So we open this one up. So here, and we should write down is again we should write down is VA equal to VC. And this is VC. For here, you can have two equations. VA is one equation. VC is another equation. Okay. So after you get this one, and then hold on, and then you get this is VA. All right, VA equal to VC. Okay, and then after you get VA equal to VC, and then we have studied the force in these points. This point C, the car have a mass, gravity force, and also Cherenkov reaction force. So there's because you point up is your positive direction. So equal to m minus mg, but they have a mg. They have a radial direction acceleration because they have a velocity here. So VC square divided by rho c. Okay, divided by rho c, and which is VC square. VC square is this one. We know this one. VC square here. Get rid of VC square is this one. Divided by rho c. This is your acceleration, m acceleration. So nc minus mg equal to m times centripetal velocity, right? Or v square equal to VC square divided by rho c. And then from here you get this reaction force equal to mg plus m times this one. You take mg out. And take the rho c out, and then you get final result rho c plus rho b plus 2h. That's the final result. Okay, to solve this problem is we have to use the energy conservation. Okay, from here the kinematic energy should be equal to this positive kinematic. This positive kinematic energy have a potential energy plus kinetic energy. Okay, and at this point they have to meet gravity force equal to the centrifugal force. That's this important. Okay, and then you get another C because another C pretty much the same formula. Only difference this VA, this VC. So VC straight away this equation should be equal to VA straight away. Okay, then we study at this point the track reaction force. Reaction force minus G should be equal to MA, and MAA have a centripetal acceleration, which is VC squared divided by R, MVC divided. So NC minus MG equal to VC squared minus divided by rho C. Okay, this is MR, And from this relationship, you can find NC equal to mg plus m central peak of acceleration. Okay, and you take mg out, you can get this result. That's how you solve this problem. Okay, then we have to go to the next question, question 4. Question 4 said this automobile having a mass of 2 megagram, which is 2,000 kilogram, 2 ton, travel up to 7-degree slope, 7-degree slopes, 7-degree slope at constant speed 1,000 kilometer per hour. If constant speed means horizontal direction, they have to balance no sigma f equal to 0. Otherwise, they have acceleration because only Newton know, right? Because constant speed it means the sigma f this direction should be equal to 0. Okay. If mechanical friction and wind resistance are ignored, okay, determine the power developed by the engine. If the automobile have an efficiency eta equal to 65%. Okay, so you have get what is traction power or traction power of the car, and use the traction power. You know the general traction power. You have efficiency and how much engine have to develop how much power. Then use the traction power divided by this efficiency. Then you get engine how much power should be get from engine, right? Because engine have some kinds of crank slide mechanism, friction, and over pumping loss there. That's why you have a so traction power not equal to engine power. Okay, so you have to divide by this efficiency. Okay, how we start that? From here we start to do the force analysis first. Sigma fx equals 0, sigma fy equals 0. We look at force analysis. So we have force analysis. This is car, and this direction you can sigma. This is traction force. And then this is a reaction force, and then you have the gravity force. You have the two projection. One is this direction project gy and gx, and ideally they should have the friction force. Friction force opposite to your driving direction. But luckily, and in this case, because it is constant speed, so sigma in this direction, sigma f equals 0. That's why equal to 0. That's why F equal to friction force plus the gx. Gx mg sine 7 degree. All right, and this F equal to reaction force times coefficient, friction coefficient equal to mg sine 7 degree. Okay, and this is for this direction. For this direction, y direction should be equal to n equal to gy, which is g cosine 7 degree. Okay, this is sigma fx equal to 0, sigma fy equal to 0. Okay. In our case, our friction equal to 0 in this case. This is y equal to 0. So the f equal to mg 7 degrees. It's pretty simple straight away. Okay. If you know f, you know v, multiply, you get the power to traction power. Force time velocity traction power. You put your m, okay, 2000 and okay times 9.8. This is this 9.8. Okay, this is how much the f mg, this mg times sine 7 degree. Okay, and that times the v is 100 kilometer per hour. Kilometers 1,000 per hour is 3,600 make SI units. You calculate all lots to get this result, this power, and this power, this traction power. In order to get the engine power, you have to divide by 65% the efficiency. Then you get the 102.0786 kilowatts. So we check the calculation. So we get equal to 2,000. Equal. Don't forget equal. Otherwise you won't get the result. 2,000 multiply 9.8. Okay. Multiply by. Remember the 7 degree is not radial, has changed radial. Multiply pi divided by 180. Okay, that's why I multiply 1,000, 100, 100, this 100 kilometer per hour, and change the SI unit 1,000 meter divided by 3,600. And this one should be give you this result. Hold on, a little tricky. 2009.8, 7 degree, pi 180. Hold on. 180 times 3,000 2000 times 6, okay, multiply, divide this one side, 1000 divides 3000, that's fine, that's fine. And this one, and then you get efficiency should be equal to this one divided by 65%, right? 0.65. And this is might get 1 5%, and divided by 1000, because this is give you, this only give you, hold on, this is give you the what, give you the watts, and the kilowatts have divided 1000 watts, and they 1276. Okay, I think this one calculation is not right. Numbers should right. I have to change it. Sorry about that. So we go to here. This one should be here. This is your results. And after your calculation, this one divided by C, and it should be get this one. So yeah, this one, and then you said this is watts. How much kilowatts? You can further down. Kilowatts is 66 and 35109 watts. And this kilowatt divided by 65 and equal to 102 kilowatts. That's how you get come from. All right. Okay, this is this question. And then we go to next question. Next question will be question 5. There's 1 kilogram block. It's given initial velocity 6 meters per second, initial velocity. And when it's at A position, if spring have an unstretched length, 0.6, this position unstretched. Okay, and then a stiffness of 1,500 Newton meter, the stiffness. Determine velocity of block when SC move down 0.3 meter. Okay, so for this issue, you typically use the principle is conservation of energy. For this position, they have a kinematic energy, half of mv square. And here, they have no spring potential energy because of the unstretched. But here is the top, highest position, because you move to this position. Here you have a height s, so you have to have a gravity potential energy mgh. So mgh plus half of mv squared. This is total energy for the position A. And you move to position C. Position C, you lost your potential energy of gravity potential energy, but you get another kinetic energy, half of mvc squared. But here, this unstretched, after go to this position, this spring stretch. So what is the deformation? Deformation should be used 0.6 square plus this s square root, and equal to this the length, and minus 0.6 make the stretch length, and multiply the k, and this will be your half of k delta length, delta x square. This is the spring potential energy. So in this position, you have the spring potential energy and the kinetic energy. In this position, you have the gravity potential energy plus kinetic energy. They have the conservation. This position total energy equal to this position total energy. So we write down this one. So position 1, you have mgh plus the half of mv square. mgh, this s. Okay, this is this position total energy. And this position total energy is this kinetic energy plus this spring potential energy. This potential energy half of k times delta x. What is delta x? Delta x is this one minus this one. What is this one? This one should be s square plus 0.6 square root, and minus original the spring length 0.6. This is delta x square. That's why you get the spring the potential energy. Okay, this is energy conservation. And from this equation, and you can multiply half m, multiply half m, and then divide by m over, and then you get Vc equal to this one minus this ends. Okay, plus m cancel this, multiply 2 and cancel the m, 2gs. And put all this number inside. K is 1,500 and m is 1 kilogram, right? S is 0.6, and VA is 6 meter per second square, and GS is 0.3. I put it inside and can calculate. I can check calculation equal to SQRT. QRT is 36 square, okay? Minus 15500. Okay? And multiply brackets, and then SQRT. And inside is 0.6 plus 0.3. Okay, 0.6 S 0.3. That's the square root. Okay, square roots, and then although this one, and then minus 0.6, and this one minus 0.6, and then make a square. Okay, and then plus 2g 2 multiply 9.8 and multiply 0.3. Okay, this is a bracket again, and this brackets for the 0.3. Okay, and this one you can enter. You get 5.98. 5.98. I get these results. Okay. All right. We have a 10 minutes break. We continue. Okay. 10 minutes break. So we finish this one. We have 10 minutes break. We continue this one. Okay.
Are essential to species. On the reef, sex, one elegant rest of the year. Priority. Garden life. They inspect drifting particles. Some are food, not just parts of other reef. In the quiet lagoon, everyone affected by somebody. A goldfish snuffles industriously. In a self-made sandstorm, it's on small masts, which locates using sensitive particles. Heavy movements are sea. The basic design is around the lagoon. They push sand in one end and out the other. Some sea cucumbers want the reef sticky feet, passing edible particles in their mouths. Nature constantly tests and refines its designs. The basic theme remains, only the detail varies. With its body completely buried in sand, another sea cucumber unfurls its feathery arms to net drifting debris. Sand production is aided by heavy-jawed grazers like the buffhead parrotfish. Moving in herds like buffalo over the reef, they bite off pieces of coral, crush it to powder, and leave clouds of new sand in their wake. The reef supports an endless variety of grazers, scrapers, and biters. Many seem to bite a dead reef that are actually cropping back a fuzz of algae that grows by day. The wastes of these school fishes act as fertilizer to the plants they crop. Water surrounding the reef is full of nutrients, so recycling of its limited resources is essential. It begins with the invisible haze of life called plankton. It continually showers the reef. Just as plankton gather nutrients from the ocean, fish like the spiny chromis gather plankton, so nutrients from the ocean are imported into the reef's economy. Boys like ghostly daggers, barracuda prove the coral fringe. They are after more than planktonic prey. These larger predators are drawn to the rich life of the reef. Compared to the impoverished oceans, the reef is a prosperous economy. Built up from nothing by the labors of tiny animals and plants, it attracts investment from thousands of other species. It becomes a bank or a storehouse of the ocean's resources. But some creatures are a storehouse of themselves. A sleek manta ray wings its way through the late afternoon. It owes its huge bulk and wingspan of 5 meters to the millions of minute plankton it sips from tropical waters. Mantas are free agents, opportunists. They exploit the reef as and when it focuses their supply. They feed and then move on, leaving each reef a little poorer for their passing. The blubber jelly voyages in the wind of wind and tide, feeding on plankton as it drifts. Billowing currents, it's an occasional visitor to the reef. Like all jellyfish, it's a free-living relative of the unmoving corals on the reef below. Building on the skeletons of others, hard corals extract calcium from seawater. Tiny polyps toil in limestone to craft their biological works of art.
stop it, and I think catch another I think a tendency. Oh, now it's lots. Very good. How can we can you catch another one? This one. We go to the pent. Okay, this is one. Nice pendant. Okay, hold on. Just stop the alarm. And this one is make sure it's last is not miss anything. Okay. Okay. So this one we should save as, and this one, and this is this B. And make sure the last one Zachary, and also Zachary. After Zachary, oh, I have another two, so I make another one. Sorry, otherwise I miss the two. Mr. Two. Okay. Maybe I can find a better way for. Okay. Zachary, sorry. Are there any some okay. Make a caption. Okay, I don't think so. Do that. Okay, I have a find the tendency attached panel. Okay, I don't think so. So this one. Make this one had another one too. Okay, we go to here. Make another one. Okay, this is should be saved as and save as JPG, right? And this is C. Continue, and then we go to okay. So basically, this week 4 question is focus on the work and energy. So use the conservation of energy. Work of a force. This force including variable force, constant force, weight, or spring force. So any kinetic energy, half mv squared. Principle of work and principle, power and efficiency, and the potential energy, which gravity potential or spring potential. Okay, and those conservation energy. That's based for, we just this principle we study. Okay, for this week 4. Week 4. Okay, we have last question. Last question is we have the 7 kilogram weights. We have 2 spring in series connection. Okay, asks you is attached 2 spring in series connection touch with the weight 7 kilogram, and if cylinder is released from the rest and release, and the spring are both unstretched at the beginning, and after release, and determine the maximum stretch for spring 1, spring 2, x1, x2. Ask you to do that. So this first position, when it's unstretched with here before you release, you have at the beginning there's no stretch, so that's why the potential energy of spring equal to 0. Half of k1 x 0, displacement equal to 0, and x2 is equal to 0. That's spring potential energy equal to 0 because it's unscratched in the beginning. And then, but you at the end of this after release, this one will move down. Spring 1 is x1, spring 2 is stretching x2, x1 plus x2. Okay, that's the distance you travel, which you have a gravity potential energy. So mgh bracket x1 plus x2. That's your initial for the rest, this position, the gravity potential energy. Okay, and this potential energy should be converted into the second position with the spring stretch. Spring stretch, you have a spring potential energy, which is half of k1 x1 square, half of k2 x2 square. And this spring stretch energy should equal to your gravity potential energy, which is mg x1 plus x2. That's the whole principle. How can solve this problem? So we go to here, and the beginning, we have mg x1 plus x2. This is gravity potential energy, and the first position with this one without any deformation from the rest. Release. After release, there will be stretch. Stretch become x1, x2. After stretch, you get a spring potential energy, a spring potential energy x2. These two spring second position, spring potential energy equal to the gravity potential energy. Okay, this is the equation. But also, we know that the force here have no mass. The force of k1, k1x1, this stretched force of the in the spring 1, and the force in the spring 2, stretch force should equal to each other. Okay, because they have force, you have to make a force balance. They have the force here, tension force equal to the spring force. This tension force here equal to spring force. That's force equal to each other. Then you can solve the x1 equal to k2 divided by k1 x2, and put this one inside, and you can see replace the k1 by this one. Okay, with k1 by this one, and then make a square. Okay, so this one half of then you take this one k1, put here, take the x2 common term outside, x2 square common term inside is this one, and then this k1 put here, you common x2 take it out, because k1 divided by k2 divided by plus 1, this one. Okay, and this one you take the k2 come out, common set k2 come out, the rest of it cancel. So that's why you get x2, you cancel x2, another x2, x2 equal to this one will be divided by k2, and this one cancelled become mg. So 2mg, 2 multiply here, 2mg divided by k2. Okay, the same, if you know the x2 like that, and this one multiply k2 divided by k1, cancel k2, then it's m2g k1, this is x1. So put this m equal to 7, 2, as 2 multiply 7 kilogram, multiply 9.8. K2 is 375, and K1 is 250. You put inside, calculate. This is x1 equal to 0.55. X2 is 0.37, and you can see your results. 37 and 0.5, get the same results. Okay, this is week 4. Week 4 our review. Okay, we finished close to week 4 review, and then we move to the finally this one we have to save. Okay, later on. Then we move to the next one is week 9. So we get the workshop 3 formally. So week 9, first question, and the solution is week 9. Okay. So the question is here, you have a jet aircraft as a mass of 22,000 kilogram or 22 megagram. Have a central gravity G is here. And if the towing cable is attached to the up position of the nose wheel, this nose wheel, up position nose wheel, and this towing cable. Okay, and this tension force exists. Tension force is 400 Newton, and this is 30 degree. Okay, 400 Newton, and this is nose wheel, and this is called wind wheel, right? And this is a nose wheel, and also determine the acceleration of the plane and the normal reaction on the nose wheel, and one of the two wind wheel. This is wind wheel, to reaction wind wheel, all right? And at the location B, and ignore the lifting force of the wind and the mass of the wheel. And this is the question. Okay. So now we have the center of gravity here. We have a nose wheel. We have a wind wheel. Okay. We have the cable pull from the top of the nose wheel, T 400, and this angle will be 30 degrees. Okay. And yeah, then we have this we have the dimension here. This is the height will be from center of gravity to this position. Height will be 0.4 meter, and this from this nose wheel to center of gravity 6 meter, right? And from this one, this point to this height, ground height is will be 0.8 meter. Okay, and from the wind wheel to the center of gravity position is 3 meter. That's what we know. Okay. For this one, we have to study force analysis first. Okay, what is force? You have a gravity force. You have a reaction force. You have the cable pulling T cosine theta horizontal pulling force and the vertical pulling force. Okay, ideally, you pull in this direction, you have some friction force, but friction we ignore the friction. We not consider friction in this case. Okay, and then you have this force. You can sigma fx equal to 0 horizontal. Fx equal to 0, sigma Fy equal to 0, and sigma rotation mg equal to 0. You have 3 equations. You should be solved all this problem. Okay, because you have unknown reaction force A, MB, 2 unknown, right? Okay, 2 unknown. You have to determine acceleration. Also, acceleration 3 unknown acceleration. So 3 unknown, 3 equations should be solved this problem. And this is how you do it. This problem. Okay, we come to here. So we do force analysis. You have a gravity force, you have reaction force, Na, Mb, reaction gravity force, and also you have force T's here. So sigma, and this one actually I should remove a little bit. This is not quite nice, not quite vertical. Yeah, make it vertical, right? Vertical a little bit. Okay, we assume the coordinate will be this horizontal positive, this vertical positive. Okay, sigma Fy equals 0. Then you have Na positive, and 2, because 2 we are left hand side, right hand side, 2 MB and the minus G. Okay, minus G, because this G is go down, it's opposite to positive. And also you have a T sine 30 degree pull down, that's a minus T sine degree. Okay, this is a sigma y, sigma Fy equal to 0. This sigma y equal to 0. It's vertical direction. And the horizontal direction, you have a T cosine 30 degree, but this one is pull this direction, opposite this to the positive, was minus T cosine 30 degree. Okay, and because you go this one, they have friction here, the mu A is friction, you moved here to go to here, friction go to this direction, so positive, so mu this friction. And also wind wheel, you move this direction, the friction should be like that, opposite, right? And the wind wheel should be used mu times MB, 2 mu MB. Okay, this is should be positive, because positive assume to from left and right is positive. And then this positive, and then this pulling force negative T cosine theta. And this one sigma Fx equal to Ma. M is the total mass of this airplane. A is the acceleration. But in our case, we not consider friction. This all equal to 0. So you only left is minus T cosine 30 degree Ma. And from this we know the 400 and the cosine 30 degree, and this M we know is 22,000 kilogram. Okay, and then put the number inside, you will get acceleration. Acceleration minus, because it's opposite to the positive direction. Go this direction, get the acceleration. Okay, so then we go to, after that, we already solved the acceleration. Next one, we have to solve the reaction force. So reaction force, we take this one as a rotation center, take the sigma m equals 0. Okay, sigma m equals 0. So we assume the clockwise is positive, anti-clockwise is negative. So we see that, and T cosine, okay, T cosine 30 degree is this one, and times 0.4, this clockwise positive. Okay, and then also from the district T sine theta go to here, and the minus Na. Okay, so use Na minus T sine theta, Na minus T sine theta, and times this distance 6 meter, and this go to clockwise. Okay, And this clockwise and at this clockwise, what is anti-clockwise? It's MB multiplied this distance. You have 2 MB distance 3 times 3. This anti-clockwise. That's why you get a negative, right? Ideally, this is NA is clockwise. Ideally, this T sine theta, this point down, this anti-clockwise. That's why you get a negative here, right? That's tell that. And then from this equation, you have moved this equation. From this equation, you can do the NA. Okay, NA, you have to move this one. Hold on, how can we solve this one? NA is equal to, okay, so this is a sigma moment equal to 0, right? And also move this equation down from here, move down. So you NA, you move down, this one mg moved over, and T, this one moved over, and minus 2 MB. That's why from this equation come from this equation. And then you replace the and this equation, and then you in this equation you replace NA by this NA. So this cancel this T sine theta. So this bracket inside only have these two left. These two left, multiply 6 and minus 2 MB3. And from here you get this is 2 MB, this is 6 MB, become 6 MB. This is 12 MB. This 6 MB, this 18 MB. Move over another side. This is T sine cosine 30 degree multiplied 0.4, and this was 6 mg. This is this side. Okay, so they go 16 MB equal to this plus this one. And from here, and then you get the MB equal to this one divided by 18. So you put this 400 cosine 30 degree multiply 0.4 and plus 6, and the mg is 22,000 multiply 9.8 divided by 18. Okay, this is your result. This result equal to this Newton and this kilonewton, right? And after you get MB and use NA, use mg minus MB and 2 MB and plus T sine theta. So you put this one 22,000 times 9.8 minus 2 MB, put the MB here, and then MB use SI units 71,874 SI units, and the plus T, okay, sine theta is 0.5, sine 30 degrees is 0.5, and sum together is to 72.05 kilonewton. Okay, this one kilonewton equal to this one and divide by 1,000 kilonewton. We can check if it's right or not right in our Excel file. You can see that. So equal to brackets 400 multiply cosine m, change this degree, change to the radial, F4. Okay, and multiply 0.4 and the plus 6 multiply 22,000 multiply 9.8. Okay, and then bracket is numeric and divide by 18. Okay, divide by 18. So you should get this one, and this one is Newton. You have to divide by 1,000 because kilonewton. Divided by 1,000. Kilonewton is 71.87 kilonewton, right? And then after that, then you calculate. So this is NB. What is NA? NA, you use this formula, which is this formula, and this is MB. NA should be equal to 22,000 multiply 9.8. Okay, minus 2 multiply 7. So you have to copy. You save time. You use this one. Direct select this way. SI units. Okay, don't use kilonewton. And then select this one. The plus 400 multiply 0.4, and this one should be your result. 72,051 Newton. How much kilonewton? Use this one divided by 1,000 kilonewton. And this gives you 72.05 kilonewton. So 71 71.8, 72, and that's we get 71.9 and 72. That's right, very close. And this acceleration 0.016, and acceleration we get not this one. We get not this one. We get acceleration equal to 0.016, right? Approximately. Okay, this up to the point to the left hand side direction. That's got the negative. Okay. Okay, then we go to next question. Question 2 for the lecture for the week 9. Question 2 is about the 10 kilogram wheel have radius of gyration Ka 225 millimeter. Okay, you know the m, you know the radius of gyration. So m Ka square. That's called a rotation initial. Straight away you can find that from your brain. Okay, and the subject to the moments, you have the moments. Okay, moments m equal to 4 Newton meter as shown. Determine angular velocity in t equal to 2 seconds. It's straight away you can see that you have the moments m multiplied time is angular moments, right? Or called angular impulse moments. Okay, should be equal to I omega. You start from 0. There's I omega. Omega is you want to find. What is I? I is mka square. Straight away you can find omega. Straight away, very simple. So we can, how can we solve this one? So we can go to here, question 2. So you have mt delta t, your moment times delta t, impulse, moment impulse equal to I omega. Okay, I is mk square omega. You can straight away use t is delta t is 2 seconds from 0 to 2 seconds. Okay, then 4 multiply 4. This 4 is your m. Multiply 2 divided by k is 10 kilogram, and the Ka is 0.06, and they get 15.8047. This straight away. Okay, or you can use a different way. You can m equal to I omega dot dot. Right? I we know that you can, from this one you can solve the what is theta dot dot. Theta dot dot equal m4 divided by m k, you get the acceleration. Okay, this is acceleration for after you apply the moment acceleration. You know the acceleration, then you should find what is omega. Omega equal to theta dot dot t. T is 2 seconds. And you multiply, you get the same result. Okay. And then also here we ask another question is also determine the angular velocity. Start from the and also calculate the reaction at the point A. That's another question. So for point A reaction, you have the gravity force and also reaction force. Okay, and you don't have the force in the sigma m minus g. You don't have the m minus g equal to 0. So you sigma fy equal to 0. So m minus g. You don't have to, cannot move at all. So they don't have the acceleration. Okay, you don't have acceleration. That's why m minus mg equal to 0. So ny equal to the weight of this rotation wheel equal to 98 Newton. Okay, because you get a 10 multiplied 9.8, you get the 98 Newton. That's sigma fx equal to 0. There's no force in horizontal. That's why nx equal to 0. Ny you have 98, which is equal to the weight of the wheel. Okay, that's this question. And then we move to question 3. Question 3 is you have 2 people, and also 2 people apply the constant vertical force. For A is 200, for B is 150. Okay, and at ends of A and B of a uniform plank, which has a mass of 25 kilogram. Okay, if the plank is origin at rest, okay, determine acceleration at center and angular acceleration. Assume the plank to be a slender law. So a slender law. Okay. So how can we solve this one? You have force sigma f equal to ma. You know the m, sigma f, you know a acceleration straight away. You can find the acceleration, which is the central gravity acceleration. Okay. Another one, sigma m equal to 0. And along the central gravity, sigma m moment equal to 0. Moment is this force times the half of the middle point, half of the slender, which is this one multiply half this length, half of length 2.5. This is clockwise and this is anti-clockwise. Okay, clockwise and anti-clockwise sigma m should be equal to I and theta dot dot. Okay, I, what is I? For this law, this rotation initial will be 1/12 ml square. That's the I. And the theta dot dot is going to be solved. And then you can find what is theta dot dot. Rotation, angular rotation acceleration. So how we solve this problem? So we come here. So we have sigma Fy equal to 0, which is 20 plus 150. And the minus mg equal to m times a. You solve this a equal to this 300 plus to get 350 minus 25, 9.8 divided by 25. You get 4.2. That's central gravity acceleration straight away. Use Newton law. Okay, and then you take this the central gravity, this point G point to sigma m equal to 0, which is you have 20 clockwise multiply 2.5. And this one's clockwise and anti-clockwise 150 multiplied 2.5. Anti-clockwise is negative. And this sigma m should be equal to I for this law. I rotation initial should be ml squared divided by 12 and multiply theta dot dot. This rotation the angular acceleration. And from this one you can take the 2.5 out, comma 2.5 out. 200 minus 150 become 50. 50 times 2.5 you get, and then 12 multiply over and divided by ml square. M is 25, L is 5, and then you can calculate theta dot dot equal to 2.5. That's how you get 2.5 the results. So you can get y is 4.2, 2.4. Sorry, 2.4. So 4.2, 2.4, 4.2, 2.4. 2.4 or 2.5. You get 2.5, get 2.4, little bit difference. Okay, 2.4. We can double check which one is right. Okay, so we double check. And this is okay. This is a little bit different. We can go to equal to this decimal problem. I think it's 550 multiply 2.5 multiply 12 divided by you can use brackets 25 multiply 25. 2.4. I get the 2.4. I don't know why they get 2.5, but it's okay. Decimal issue. Okay. All right. Then we go to move the questions 4. What's the question 4? Question 4 is low holola. This you make some kinds of trim the low edge. Use this kind of tools. Okay. These have a mass of 80 kilogram mass. I have a radial of duration of 0.75. You know the mass, you know the radial of duration, you know the I equal to m kg square. Straight away you can reaction this initial rotation initial. If it push towards at force 200 Newton pushed towards, and then there's instantaneous rotation center should be A. Okay, you push towards, and then this because the rotation is A, this tangential, this instantaneous speed of G should be this omega multiply this radial. Okay, omega multiply radial, or this acceleration, the instantaneous acceleration should be angular acceleration multiply this radial. That's how it works there. Okay, so 200 Newton, you can have a components cosine 45 become horizontal, and tangent and the tangent 45 sine 45 become the vertical direction. Okay, vertical you have gravity force, reaction force, and also have the force component from 200 in the vertical projection. There are 3 forces in the vertical direction. But horizontal, you have 200 cosine 45. This is one component here. Okay, this, and also you have friction. Friction go to here. Friction there from there. You move this direction, friction should be go this direction. So you have a 200 cosine 45 minus this friction equal to ma. Okay, it's gravity center mass and multiply A, gravity center, moving to this direction. That's how you solve, okay? Determine angular acceleration, this one. And also coefficient of static, the kinematic coefficient is static is 0.12, and is a motion or kinematic friction coefficient 0.1. So we can calculate this from force balance. We can calculate this friction, and you can see if it's more than this the critical, and because you get a motion, get m, get a static maximum static friction, and also motion friction. Which one is larger? We can make comparison. So how can we solve this one? We solve this one again. We get sigma f x equal to 0, sigma fy equal to 0, and notation sigma m equal to 0. You have 3 equations. You can solve all problem. So we come back how to do that. So we come back sigma mg, start from sigma mg. Sigma mg is you have a I is mk g square multiply theta dot dot, and this is your sigma mg. This is your I theta. So in this case, what is m? What is moments? Moment from you start here. This one past the center of gravity, no movement. This one past center of gravity, no movement. Only have this force. This force have friction. You move this one to friction. Friction times this distance have the moments. Okay, so that's why because Fs times r, Fs times r equal to I theta dot dot, and you solved out Fs equal to this one divided by r radial. This one divided over the radial. Then straight away you find the Fs. Okay, step 1. And then we start this sigma horizontal Fx equal to 0. Horizontal we have a we assume this one is positive and this one is positive. Horizontal is 200 cosine 45 is positive. Okay, and the minus you have Fs friction. Fs friction you replace by this one. Then they only have this one horizontal component minus Fs is equal to mag, right? You replace Fs by this one, and then from here, and then you can solve. And in this instance, we have a angular acceleration theta dot dot. Okay, and the rotation is here. Rotation here is r times theta dot dot equal to ag, which is a linear acceleration. So the mg should equal to r theta dot dot, and then you put this one inside, mr r dot dot, this mg inside, and then you should be able to solve what is theta dot dot. You move over, take the common things out, theta dot out, divide by over, and this one should be 200 cosine 45, and this one you take common things out, theta dot out, inside is mr m. You can take m common m is 80 kilogram r, inside is r is 0.2. Okay, and the kg square is 0.175 square divided by 0.2, right? And this one you put inside, you can calculate equal to 5 radian per second square. Okay, we can check if it's right or not right. So we go to the equal 200 equal, be careful, equal 200 multiply cosine 45. Be careful, this is 45 degree. You have to get the radial. Pi divided by 180. This is numeric, and divided by brackets 80 multiply, and the bracket again 0.2 plus and 0.75 square. Okay, and divided by 0.2. This is numeric. So, and then how much you get? They have a little bracket missing. Okay, they automatically check for you. Don't worry. This one you get exactly the same for 5.00 radian per second scale. After you get a theta dot dot, and then you already started sigma fx equal to 0, sigma m equal to left. One left is vertical. Vertical sigma fy equals 0. Y is reaction force m minus this the force of 200 force at the projection on the vertical direction. This one, so this is 200 cosine 45 minus 2 cosine 45, and then or cosine or sine doesn't matter because cosine 45, sine 45 equal to each other. Okay, and the minus mg minus because vertical you have weights, and this one should be equal to 0. Vertical direction force should be 0 because vertical you cannot accelerate. That's why equal to ma acceleration equal to 0. That equal to 0. Okay, and from here you can find what is n. N moved over 2000 sine 45 plus mg. 80 times 9.8 equal to 925 Newton. Okay, then after you get the n, interesting, you multiply the static coefficient equal to 111. Multiply kinematic coefficient is 92. Both of these force larger than your calculates, use this formula calculates 61. So it means this one, the point, this friction is much less than your maximum static friction or kinematic friction. Then it means there's no slip here. They all it's purely lonely, no slip here. Okay, that's you get the results. So you get final results 5 radian per second, 5.4. I get 5. A little bit difference. I don't know why, but anyway, he gets the result is 5.4 radian per second square. I get is 5.026. Yeah, that's a little bit difference. Okay, and yeah, if you get a different result, let me know. But this is what I get result. All right, this is what I get results. All right, maybe this one is wrong. Result is not quite good, correct, or maybe something wrong with me, my calculation. Maybe, but so far I cannot find anything wrong with my calculation. Okay, that's I believe I'm right. So we get the 0.175. Okay, that's why a little bit different. Or 0.5, and he gets is 5.4. Little bit difference. Right. Okay, so this is week 9 question. Okay, so do you have any question for week 9? If not, we have to move to week 10. Do you have any question for that? If not, I have to move to week 10. Okay, so we go to week 10. And week 10. Week 10, this question 1. Week 10, this question. So the question 1. This is this mechanism. Week 10, first question. Week 10 said this link A and AB and CD, they have a mass 1.5 kilogram. And you have link BC. Okay, because this is a sphere, and this BC will be moved with actually it's a linear motion. It's no rotation. Okay, and then the link BC have a mass of 2 kilograms. Determine kinetic energy of the mechanism and at the instant 30 degree instance, and if omega AB equal to 3 radian per second is maintained. Ask is kinetic energy constant for the general theta or not? General theta or not? Okay, so we try to solve this issue. So first of all, we have this rigid body. You have center of gravity velocity calculated from the omega multiplied half length, center of gravity half length. So half length, half of AB multiply omega AB. Okay, it's equal to this 2 divided by 2 is 1 times 3. You get the 3. This gravity the central gravity velocity. The same thing for DC is the same, should be same. All right, and then for the BC, this velocity should be this point BC, right? Because omega times 2, double of the 6, the 6, and this is also 6. So any point should be 6 for that. It's 6. Okay, then we get all central gravity velocity 1, 2, 3 central gravity velocity. And then the total kinematic energy should be equal to 2 TAB, the 2 bar kinetic energy plus the middle one. Okay, so 2 will be for this 1 bar, there is kinetic energy equal to central gravity energy. Okay, central gravity energy, central gravity, the kinetic energy, half of mv square, plus this rotational kinematic energy, which is Ig, which is equal to half of Ig omega square. That's the formula. Okay, and this is because these two exactly same multiplied 2, and then for this one you have the center motion is half of mbc, mass times central gravity, because the move is a translation move. So this one should be equal to VGBC, right? VGBC. Okay. So in this case, in order to find the general case, we have to do something for the general case, not 30 degree. I assume 30 degree we can see for that. So for general case, we have look. And the general case, have look. So open this one. So open this one. So if the general case should be equal to, and you could like that. So this one should be EK for general, not 30 degree. We have look general case. EK should be equal to this one. And for this one, VGAB in this case will be omega for general case, omega, right? It should be equal to this one, general case, and this omega. And also this, the AB, and this one is I should be theta dot. Theta dot also is okay. And this general case should be omega AB, should be okay. So this one should be equal to, then you get the energy should be, I think energy should be conservation for that, right? For the general. So you have put this 2 multiplied by half of MAB is 1.5, okay? And then plus as half of this is V square is 3, square is 9, okay? Half is half, and then IGB is here, is half here. IGB is half. IGB is half. Half multiplied by half is 0.25, and theta dot is omega is 3 squared become 9, and this one's this 2, the horizontal BC mass is 2 divided by 2, and multiply this VGBC equal to 6 square equals 36, multiplied for 55G. Okay, 55G. Then this is 30 degree. For any angle, what happened? For any angle, so any angle you have, I think we should understand any angle, and any is constant for general theta. Answer the general theta or not? General, I don't think so, because there were potential energy will be changing, so they will not be constant. You know why? Because here this is the position of central gravity, the 30 degree. You go to the position, this position, and you see the position changing. This the potential energy of the MGH, they will changing, right? The changing, if the change in the potential energy, of course, they will convert this potential energy into kinematic energy. So this kinematic energy will not be constant for general angle, because they will invert the conversion between the kinematic energy and also the potential energy of gravity. Okay, that's simply answer for that. Okay. Okay, simple answer like that. Okay, the result is 45 degree, 54 degree, 54 joule. Okay, result is all right. So because you in this case you have to convert different position theta, different theta, the potential energy of gravity potential we are changing. Okay, the total energy, gravity energy, and also kinematic energy, total energy should be conservation. Okay, so that's why, because your gravity energy will changing, that's why your kinematic energy also will changing, because some of the kinematic energy and the gravity potential energy, some of them should be conservation, should be constants. Okay, the simple answer. Then we go to question 2. Question 2 is a pendulum of the choppy impact machine has a mass of 50 kilogram and also have a radius of gyration Ka equal to 1.75. You know M, you know the Ka, and M Ka square, you get the rotation initial. Straight away, you get the rotation initial. If it is released from the 0 degree from here, horizontal release, and then determine angular velocity before you hit this spaceman S, hit here. Okay, so from here you get the potential energy of gravity potential energy, mgh. You get it. This one should be equal to this is L, okay, L for here, okay, L, and then should be L should be from here. So this distance, mgh, this distance, this is potential energy. Okay, and then after hit here, you this potential energy should be equal to here. This should be have a kinematic energy, half of mv square, half of m square. This point, G point, have velocity half of mv square kinetic energy plus the rotation ig, you know, initial and theta dot. You know, tangential velocity divided by radius equal to theta dot. Okay, so half of I theta dot square. This is this rotation kinetic energy plus the center of gravity, the velocity, half of mg vg square. That's get the conservation equal to the mgh, which is h is this one for the initial gravity energy. That's how solve this problem. So we come the solution. So we can get mgl, this L, mgl. You put the 0 position from come to here, the whole mgl, and should be converted to the first is central gravity velocity, which is L times omega m, which is tangential velocity, half m v square. Okay, this is central gravity point velocity, m v square, and rotational kinematic energy, which is half of I omega square. Get the two energy together. So you cancel the m, and you get a GL equal to this one, and then you solve take the omega square common things out, multiply 2 go to here, and then you calculate omega square should be equal to 2GL divided by kg square plus L square. Omega is square roots, and you put the 2, 9.8, 1.25, 1.75 square plus L is 1.25 square, and the result is 2.30. That's the radian per second. This result for the omega. So you have what we get 2.70. 2.70. Little bit different. 2.83. I get little bit different from him. We can double check if the calculation right or not right. Okay. So equal to SQRT and 2 multiply 9.8 multiply 1.25. Okay, divided by 1.75 plus 1.25. That's the out and another bracket. This one should be equal to 2.30. That's what I get, 2.30. Okay. Unfortunately, I'm different from his results. Maybe this was something wrong, or something wrong with me. You can check, tell me which one is wrong. I believe this is right, because you have a potential, and here is stationary potential this potential energy, which is gravity, to be converted to that one. This is a central gravity point kinematic energy plus rotation along this point, rotation kinematic I omega square. This is the energy conservation. And from here, I find the omega. I think I believe I'm right. Okay. All right. Then we move to next one. Next question is question 3. Question 3 says, man having mass is 90 kilogram, okay, and sit in the chair of the ferry wheel, and exclude the man, this wheel, the ferry wheel, ferry wheel have a 7,500 kilogram, and also have a radius of duration of k0 equals 11 meter. If at torque 120 multiplied 10,000 Newton meter is applied for all, determine the angular velocity of the wheel after the rotation 180 degree. And we ignore the weights of the chair. Notice man remain in the upright position as the wheel rotates. Okay, and the wheel start from the rest in the position shown. Okay, we have 10 minutes break. We continue. Okay, 10 minutes break.
The stony skin of coralline algae glues the limestone rocks. Filamentous algae on rocks, but it's the pasture and essential to grazers. The ties that bind algae together go deep. Like algae, hard corals require sunlight to grow. This is a clue. Relationship that literally corals are edging. They're animals harness the power of plants to build the vast, elaborate limestone structures. How have they done it? Somewhere in the past, coral struck a deal with microscopic single-celled algae called zooxanthellae. Algae sheltered inside the polyp tissue, producing sugars from sunlight and recycling coral waste products. This partnership, most powerful evolutionary achievement. Between them, they built reefs. It's not until the sun sets that coral's second animal egg is revealed. As darkness, plankton nightly ascend into the waters surrounding the reef. From their sleep layers emerge bee colonies to be harnessed. Other members of the night shift emerged. Feather stars take up strategic current. They sieve plankton and particles. Slender prey, a formation of expert mimic half coral that hides their lifelike. A chaotic ball of tailed cat swarm water between the lagoon sands of delicacies. These miniature catfish, scarred for their southern rank and file, aided by sensitive chin whiskers. Lagoon settings provide dainty things for the feather-mouthed sea cucumber. Little must secretly have rubbery bodies to make them unpalatable to predators. They knew their slaves, nothing except for dead, had no. Unlike the sophisticates of the 19th, a hunter by night, an octopus labeled color and texture, hiding and blocking. This stealthy camouflage is both actor and magician. Its relative, the cuttlefish, shares the octopus color, lighting color change. Shunning camouflage altogether, flamboyant Spanish dancer bounces through the night. Its colorful costume signals predators. Like other king crabs or sea slugs, the Spanish dancer looks tastes. Overcome by darkness, parrotfish tire into the fabric of. Some of these daytime dandies sleep and blossom and grow weak. Perhaps this bubble disguises their scent, unwelcome visitors. A fast-moving vegetarian, parrotfish grazes algae with bird-like beak. Clownfish, government, their protective anemone at night. This is the breeding of shared lives. Multi-layered civilization, and its inhabitants have perfected the art of living on and in each other. Liaisons are everywhere. Some may be hard to find. Ornamented anemone harbors color coordination. Competition tough. Citizens live together. There are winners and losers. The blood-sucking fish mouse has a one-way suffering. Corals are not exempt from others. Down among the valleys lies another world that's never been seen. That world, living the coral, tiny long, weird, hiding like magic.
Okay, we continue. So how to solve this question 3? Very simple. You have applied the moments and have to rotate 180 degrees. A moment times theta is the external work. This external work will be increased the total energy level. At the beginning, this energy start from 0, right? Start from 0 at the beginning, start from 0. And then after apply this m multiplied theta, external work should be increased energy level to the top. Top is one is mgh, potential energy of gravity. Another one is that this person have a tangential velocity half of mv square, kinematic energy of the people, and also the whole wheel half of I omega square, whole wheel rotation kinetic energy. That's 3 parts. Okay, so this m times theta equal to mgh plus m half of mv square, person's kinetic energy, and also the whole wheel I half of I omega square. That's the because you apply for external work. Okay, come here how to solve this problem. So you have m times theta external work, torque times displacement external work should equal to mgh and plus half of I wheel initial and omega square, and also the person half m person are v square r omega square. Okay, so in order to find the omega, so you move this OI term to left hand side. Is to left hand side here, and then this one you take the common omega square out equal to this one. So from here you can solve the omega square equal to this multiply 2 divided by this one. Okay, so you put inside 2, m is theta is pi 180, and then the m is this 120,000, right? 120,000 is 120,000 moments. 120,000, yes, here. Okay, and then minus 2, the person is 90 kilogram, G is 9.8, radio R is 18, okay, 18, divided by, this is MKW square, the wheel 7,500 M mass, and this is K is KW, the radio for generation is radius generation KO equals 11. 11, okay, 11 square, and plus m is 90 kilogram, and the I is 18, and you put this one calculate equal this one. You can check the calculations right is not right. Okay, double check. So we go to the here equal and the square root, and then we go to numeric, right? Square root, numeric, bracket again, numeric, again, multiply, okay, and minus 2 times 90 times 9.8 times 18. Okay. And the brackets, first brackets, bracket is this for the numeric, and the dominance divided by dominance is 7500. And multiply 11. Yeah, right? Right. So 11 square, and then 11 square and plus 90 multiply 18. And then you have close the dominants and close the square roots, okay? And enter. And Mr. 1. So this is square root 2 multiply square root multiply pi, okay? Minus 2. 2 multiply, sorry, this is a plus, it's not right. 2 multiply 99.818 brackets divided by this one, 750 multiply 11 square plus 90 square. Okay, that should be all right. And this is 0.858, exactly same. So what he gets? Answer. He gets 0.86. So we get 0.858, 0.86, exactly same. Okay. So we go to question 4. What's question 4 talk about? Question 4 is there's two tugboat, one tugboat, another tugboat. They to apply constant force on this ball. One is F, another F. Okay, of course, F times distance get the moment. Okay, and these force are always perpendicular to the ship central line. Okay, if this is not it, if the ship has a mass and also radial duration, the mass times radial duration, kg square equal to rotation initial. And determine the angular velocity of ship after 10 to 90 degree. 90 degree is half of pi, right? Half of pi. So you get half of pi, and then you get the rotation initial. A ship is already in the rest. Okay, so that's you need F times distance is the moment. Moments, okay, a moment times this moments times displacement, which is moment times displacement is half of pi, then should be equal to half of I omega square, right? So because the applied external work should equal to the build-up of kinematic energy. This kinematic in this case is rotational. Half of I omega square. I is m kg square. That's how we solve this problem. So we had look how can we solve this problem. So you get Fd is moment times G. G is 2 pi, half of pi. Okay, this external work should be built up this kinetic energy, half of Ig square. I equal to kg square multiply m. Okay, so in this case, this is half of pi. Cancel the half. This get pi. So fd pi divided by I. I is m kg square, and then square root. This is what you get. That's the result. Pretty straight away. See that? It's pi fd divided mg square. That's the result. Exactly same, right? All right. Then we go to next question. What is next question? Next question, question 5. Question 5 is at instant show, this instant, 50 kilogram bar is rotating downwards. Okay, at the radial, omega is 2 radial per second. Spring is touching another end. Always remain vertical due to the lower guide at C. Okay, and if the spring has an unstretched length, is 1 meter, but now it's 2 meter. You already extend 1 meter. Delta L already have delta L. That you already have the potential energy of a spring already have stretch, and also you have and this point you have the half of I omega square. Okay, half of I omega square. You can use this center of gravity I omega square plus the center of gravity the v half of mv square this way, or you can use the rotation center of this one is whole bar rotation initial I omega square. Either way, you can do that. Okay. Then determine the angle theta measured below the horizontal. Okay, angle theta below to which when the bar rotates before it fully stop. So what's the maximum angle you can go there? Because the maximum angle when you stop, then it means this one you already extend 1 meter. Extra one, another extra one extends potential energy. Okay, this one should be equal to 3 meter times this theta. This is deformation plus 1. Half of k, this is 1 plus this is L AB and times theta. This is potential energy of the spring. Again, in this position you have MGH, which MGH is center of gravity position. So it should be half of this AB and the sine, because this AB since multiplied theta is here displacement, but you look at the center of gravity position. So half of this displacement is MGH. Okay, MGH, this position plus the kinetic energy of this bar and plus the potential energy spring, this first position, and then equal to the end position, which has another potential energy spring. Okay, and that's all, because the end you don't have the potential energy of gravity, you don't have the kinetic energy because fully stop. So they only have the pure spring kinetic potential energy equal to this position. You have a kinetic energy of spring, you have the gravity potential energy, you have spring potential energy, and you have a kinetic energy of this bar. The moving you have an omega here. So how can we solve that? So we come here. You have you have first position. This is bar. You look the central the whole bar along the center of gravity rotation initial. Okay, this one is half of I is half 1/12 ml square. This whole bar along the center of gravity rotation initial omega square. Okay, omega is 2, right? And then this is the whole bar rotation along the center of gravity. Another one, center of gravity, how does it move? Center of gravity velocity equal to half of the length multiply omega. So half length multiply, this is the center of gravity velocity. I multiply the mass and the velocity square. This is central gravity is central kinematic energy. Okay, plus rotation kinematic energy. And this is the total bar kinematic energy. And then for the spring potential energy, there's delta L, which is your initial is 1 meter, delta L is 1 meter. 2 minus 1, this delta L is a spring potential energy. Remember, you have because the last position we can get lower, and then your center of gravity actually you have distance here, MGH. MGH, this H should be equal to L sine theta divided by 2. So MGL sine theta divided by 2. L sine theta by 2. This is this position the potential energy of gravity. This one, and this have a gravity potential energy, spring potential energy, and the bar kinetic energy with rotation and also center of gravity moving kinetic energy should be equal to the second position. Only have spring potential energy, which equals L theta deformation plus the original deformation delta L and square equal to that. And from this relationship, you should be able to, and you can cancel half, cancel half. Okay, and then you should solve the theta. Okay, you should solve the theta. From here, you can solve theta. You can move the sine theta, sine square theta, and you can make this organize this equation become sine square. You assume this x square, this x. So you a x square plus b x plus c, this equation. Okay, and you learn from your high school. This should be equal to minus b plus minus b square minus 4ac divided by 2a. That's the solve this equation. Okay, and this x in this case sine theta. But this is plus minus. Why I'm not take minus? Because this one, this square root larger than this one. You take a minus, this become negative. Negative means your theta will be go to because your theta should be go this direction. They won't go to this one. It's impossible to go up. That's why you only take the positive. Okay, that's why you calculate this result equal 0.93, and C that equal to 32.28. I just checked for the calculation. So this one should be equal to sine theta, according to the formula, should be equal to brackets, that the numeric 30 and plus square root 900. Okay, and the plus 4 plus 9 plus 240 and 940 and multiply 600. And then the brackets for square roots for bracket for square root, and then have the bracket again for the numeric and divide by brackets 18 multiply 240. That's for the dominant. Okay, so what this one should be equal to 0.53. Okay, 0.53, and then you can how much you should be equal to, and this one should be equal to arctangent, arcsine, right? Arcsine one should give you give you radial, and get this radial you want to get its degree, then should be equal to get degree should be equal to that 180 divided by pi. Then you get a degree 32.278 degree. Okay, so you check what is the standard results, and then this 32.3. Yeah, get standard. It's 32.3. I get this 32.3. Yeah, that's right. Okay, so this way we end up this lecture 10. Then we go to lecture 11. Lecture 10, we end up. Lecture 11, what's happened? Lecture 11, we go to open up this question, and we open up the solution. Okay, so lecture 11, what's first question? First question said you have the gear, this driving gear, this driven gear, 3 driven gear, and 1 driving gear. Driving gear, you have m moments is 0.05. Okay, driving. Of course, if we're driving, there is the mesh have force will be against the driver, push back. Okay, push back. Okay, and then driving have to move this direction and push back. 3 force push back. Okay, and force times radial. Force times radial is resistant this movements. Okay, so ask determine the angular velocity of each of 3 smaller gear. Okay, and in 2 seconds starting from rest, and smaller gear are pinning at their center, and the mass of the central radius of gyration of the gears are given the figure. This is m, and this radius of gyration for larger gear, and this is m for radius of gyration for small gears. 3 small gears identical. Okay, so how can you solve this problem? So this problem is simple. You should get m is driving moments, and the minus 3 resistant moments equal to I omega. Okay, you know m k square. I already know that. Then you can solve this. Then you can possible get m I theta dot dot. You can get I theta dot dot. But this mesh, if you this theta dot dot a at this mesh with radial, and r a theta dot dot a should be equal to rb theta dot dot b. They have some relationship there. And for each of this small, you have f divided by r. The moment should be equal to I omega theta dot dot b. So then you can get the 2 equations, solve this 2 unknown. So how can we do that? We can check. So you have a moment like that. You have 3 the mesh force against the move. Okay, this resistance force. Okay, and then for each of action reactions, for each of small scale, you have a reaction force like that, action reaction. So for the gear mesh, RA omega should be equal to RB omega, this gear mesh. Okay, so M, this M, the moment minus 3F radial, 3F RA, resistance, the torque, equal to I is MA KA squared multiply omega A. Multiply, I think this is not omega A, should be, this should be theta. This is MIT. So this is the moment times T. Moment times this impulse, this angular impulse, moment times T should equal to I omega, right? And then, and from here, for the larger gear, so you apply the M times T equal to I omega A. This is for omega A. Then we study omega. This is small gear. Small gear, you have F times radial. This is the moment times T, same T, should equal to IB, which is MB KB square, IB, and times omega B. But omega B should be replaced by this one. Okay, so now you have two equations, this equation, and you put this omega A should be equal to this one divided by MAKA, and then you put F equal to this one divided by RB. Hold on. So F should be equal to RB squared T. Hold on. Equal to FB. This one is correct. What is F equal to? F is FB RA omega A, and this B divided by B squared. That's B squared, and divided by T is here. Okay, and then you replace the, and here you have F omega A. You use this one replace omega A. You literally replace. So F equal all this one here plus omega A. You this replace. So you open up this number inside and F inside, and you make simplify like that, and then you open this, multiply this one equal to this one. You move over this one, sum together F equal to this one, and use this one divided by this one. You get F equal to 0.21377 Newton. Okay, after you get F, and then you get omega A, put F inside. This all you know, put data inside. Omega A equal to 63.33. And after you get omega A, then omega B equal to RA divided by RB omega A. So use the omega B is RA divided by RB, which is 2. And the omega A is this one, multiplied is 126.67. So you have look and you check. We have check what is correct or not correct. We can come here, check correct or not correct. We do the his here. Check. So we can get another one to mass. Mass we can go to equal to, and there's 1, 2, 3, 1, 2, 3, 1, 3, 5 divided by 6.3152. Okay, and multiply 7 equal to 0.21377. Okay, then we calculate omega A. So omega A equal to brackets 0.05. We multiply, okay, multiply, okay, and then brackets multiply 2 divided by 8 brackets 8 That you should get. Okay. 63, okay, and then this one 2 times 61, 26. So what is the standard answer? 63 omega A, 126 omega B, double. 63.3, 63, and 126, correct? So you get the question 1 already done, okay? So summary for this, how to solve this issue, you study the gear A first. M times T, which is impulse, moment impulse, should be equal to the angular momentum increase. Start from 0 and equal to I omega. I is M K O K A square. M A K A square. This rotation initial. Omega is what you want to know. Omega A. Okay, omega A. And also for this scale, because you have 3 resistant force in the mesh position. This force times this force, meshed force, hold on. This mesh force times this RA provides the resistance torque for the A gear. But this force multiplied the radial B provides the driving force for the gear B. So FR driving FR is driving moment multiply same T should be equal to I, this IB, which is MB KB square, and multiply omega B. And omega A, omega B, the mesh relation RA omega A should be equal to RB omega B. In this case, you have a 1 equation, 2 equation, and the mesh equation, 3 equation. You can solve this 3 equation, you can get, and finally you can get omega A, omega B. That's how you solve this problem. Okay. Then we move to the next question. Question 2 is for a safety reason. A 20 kilogram supporting leg, supporting leg AB of a sign is designed to break away with a negligible resistance at B. Okay, and then when the leg is subject to the impact of car, impact here, this position 0.25. Okay, and this is 2 meter impact to this position. Okay, and then assume the leg is pin support here, pin support A, and then approximately a thin low. This is a thin low. This is a very thin low. So this height is negligible or ignore. Determine the impact of car bumper. This impact, which is F times T, determine. Okay, and apply on it. If after impact the leg appear to rotation upward to 150. Okay, that's how can we do that? We have an impact F times T, right? F times T, and F times T, then we should have if we go to angular, should times F times T. Also, you should times this radial. Then you get the M, get the moments. Okay, moments times T. This moment times T should be equal to I omega, right? I omega. And then from this I omega, we should know that, you know, the K, you should know that, hold on. This rotation initial is 1/3 of ml square times omega. Okay? Times omega, and then you should find the MT I omega. You can find what is omega. And this omega, and then you use the energy conservation. For this position, this position you have the omega I half of I omega square. This is rotation, total rotation. The kinetic energy should be equal to the 150 position. This one you maximum reach that. You have the gravity, the central gravity potential energy or gravity potential, MGH. In this case, MGH equal to this length AB cosine theta half. Cosine theta, hold on. So you go to A, this AB minus AB cosine theta. This difference, okay? You move up, because you move up is this end point, and then in the middle point you half. And this is your MGH. And this MGH should equal to half of I omega square. That's how you solve it. We can have a look. So the question 3, you can see that first you have F times this distance from 2 meter times this one. F times this is the join point, this is pivot point. This one, this distance, this is the moment times delta t equal to I omega dot. Okay, this impulse equal to angular momentum, right? And then you have energy conservation. Half of I omega dot. This is at this position, this total rotation initial. If you study, this is your pivot point. Total rotation initial I omega square should be equal to mgh. This mgh tricky is for half of L. And then half of L take out 1 minus cosine 150 divided by 80. Because 150 degree, you have to change it to the radial. So divide by, multiply pi divided by 180. So 1 minus this one. So 1 minus this one should be this distance. But this distance you have studied in the middle point. So you should divide by half. And half. Yeah. So this mgh, this gravity rotation initial should equal to this kinetic rotation kinetic energy. And then from this relationship, you can solve with theta dot. The cancel the half, and then should be able to get theta dot. Okay. So this is 1/3 of ml square. 1/3 3 multiply over 3. Okay. M can cancel L square cancel 1L become L become dominant 3G L, and this inside is 1 cosine 150 sine 180 multiply pi and square root, because theta square root. And from this one you can calculate this, you can get the theta dots. Okay. And then you this one you can this one you can use the, I prove this I equal to 1/3 of L square Y, because you go to the central gravity, the bar central gravity rotation initial. This bar central gravity rotation is 12 ml square, and the plus from this m times distance, m times distance half of L. So this is 1/4. This is 12. 1/4 means 3 divided by 12. 3 divided by 12, 3 divided by 1 plus together is 4 divided by 12. It's 1/3. That's I prove this 1/3 for this whole this bar according to this point, and the rotation initial is 1/3 ml square. Okay, that's why I already used here. That's why you cancel the m. Okay, multiply 3 here and divide by L, cancel the L here. That's why you get these results. Okay, that's where I come from. I just proved this I equal to 1/3 ml square. I already used this result from this step. Okay, then after that, and the impulse should equal to this one divided by 1.75, right? And this I is 1/3 of ml square. We already said give 1/3 ml square, and then this theta dots here. We know theta dots. Replace theta dot by this whole lot with theta dot, and this one should be 3. Put the dominant 3 multiply 1.75. M is 20. L is 2 square become 4, right? Multiply the whole lot theta dot is multiplied here. So you 9.8 divided by 2 and 1 cosine 150 and 180 pi, and you calculate this one, how much you get, and you get 79.8 Newton meter. We can check if it's right or not right. So equal to equal to I think I have 10 on the lines. It's very dark. Okay. Equal to what? Equal to 20 multiply 4. Okay. Divided by 3 and 1.75. Okay. And multiply square root. Square root is 1 is 3 multiply 9.8 divided by 2 multiply brackets 1 minus cosine 150 this degree multiply pi divided by 180 becomes radial. Okay, and this cosine is one bracket. Another one is another bracket is here, and also have square root bracket. That's all, square root bracket. That's all, and equal to 79.8. Okay, that's what the result 7.08. You check what the result for this one. 79.5. What do I get? 79.8. I have a little bit difference. Little bit different from the results. They get 75.03. I get is I get 79.8. I believe I'm right. Okay, unless you check, you tell me I'm wrong. I believe I'm right because this is according to this principle, right? So then we go to next one question 2. Then question 3. What's question 3 talk about? Question 3 talk about is a man sit on the sphere chair and hold the 2.5 kilogram mass within his arm outstretched. First is 0.75 outstretched. Make a turn his chairs. If he turning at the omega equals 3 radial per second in this position, we can turn, and this turning should be his total kinetic energy equal to I equal to half I omega square. I is get the mass times the radial of gyration square. This I and multiply omega. Okay, and this is his human body. And the plus they have two mass, 2 multiplied m. M is 2.5. Okay, 2.5 and multiply the radial. Radial is 0.75 square. That's mr square. Okay, mr square, and then this is and times mr square is rotation initial. Okay, and then multiply omega square. That's the this position. And then second position, if they make this arm make short, become 0.09. He just when his mass are drawn in and hold 0.09 from the axis of rotation, and assume you have to decide what is new angular velocity. Okay, assume he has the mass of 80 kilogram and the radius of gyration of kz equal to 0.165 meter about the z-axis. Ignore the mass of his arm and the size of the mass for the calculation. So how can we solve this problem? So again, what first position, what is the total kinetic energy? And the second position, kinetic energy, they should be equal to equal to conservation. Okay, we go to this one. Then we go to this human, right? First position is m kz, human being, I, rotation initial, plus the total mass mr square. This mass should be have 2. It should be 5. Okay, 5 kilogram. This 2.52, so 5 kilogram mr square. This is this human body rotation unit. This mass rotation initial multiply omega 1. 2 equal to omega 2. Omega 2 his stretch is 0.05 mr square. mr2, and human the rotation is not changing, and the omega 2 should make a new omega 2. We find this new omega 2. So this omega 2 should be this one divided by this lots. Okay, omega 1 we know is 3, and R1 is 0.75, M is 80, and the radial of gyration is 0.65. So M is 5, 2.5. And then the second position, radial is 0.09. The total mass is 5. So the human mass is 80, and the radius of gyration is 0.165. And then you calculate this ratio equal to 6.748. I double check if it's correct, not correct. Equal to brackets 5 multiply 0.75. Okay? 2 5, and multiply 80 This is a numeric divided by dominant. Dominic equal to 5 and plus 80 and okay. This is your dominant and multiply 3. 6.748, 6.75. Look what he gets. 6.76. Okay, a little bit difference anyway. And that's what I get, right? 6.76, I get 6.75. Okay, a little bit difference. All right. That's my results. And then we move to the next question. The next question is question 4. Question 4 says you have a pendulum consists of the 2.5 slender load, this 2.5 kilogram, and the block with 5 kilogram block, timber, wooden block. A projectile or bullets have a mass of 0.1 kilogram and fire into the center of the block, bullet, okay, and stay inside with velocity of 300 meters per second, okay. And then if a pendulum is initially at rest, after hit, you have any hit impact, and then they have the momentum balance. They have to develop the speed or rotation omega, and then should be moved up some position, stop there. Okay, so initial is rest, and the bullets imbued in itself into the block, determine angular velocity of a pendulum after impact, as omega. And maybe after this omega can be convert this energy into the potential energy of force of the gravity potential, move this go up a little bit. So how much go up we can discuss. Okay, so how can we solve this problem? We have what we have. We have this one before impact. We have mv, right? Mv is momentum. Multiply this distance to get angular momentum. Before impact angular momentum should be conservation equal to after impact angular momentum. After impact will be this m plus this m, okay, and this m, and the angular momentum we can put together, and they equal to I omega. The whole system I omega. The whole I equal to this part I equal to this central gravity rotation initial plus this mass times this distance, m(r) square and omega square. This is one part of I omega. Okay, and the second part is the law. This law, from this point, there's this law move rotation along this point. That rotation initial we know be proved before last question is 1/3 of ml square. And this 1/3 of ml square multiply omega. And this is the second part of rotation, the angular momentum. Okay, there's two parts. Okay, how can you solve this one? We come here. So first of all, you get the mv, this bullet mv, multiply this distance from this distance is 0.6 plus half of 0.3. Okay, this is arm from here and half of here, which is 0.75. Plus half is 0.75. So this angular momentum should be equal to after impact angular momentum. After impact angular momentum, I and multiply omega, right? Theta dot is omega. What is I after put together? It's one piece. The total system, what is rotation initial? There's rotation initial equal to this block, rotation initial with respect to this point. This one rotation equal to center gravity rotation initial, which if you have been here and you have a beam rotation initial for this axis and the y axis should be half of 1 over m 1 over total mass is plus the bullets, m plus small m bullets, and there's a and b. For this direction, m a square, and this direction m this direction this m make a central rotation. It's vertical to the paper, the screen surface. So that this is a half of m a square. This is half of m b square. And sum together is central point rotation initial. Okay, this is the block notation initial plus the block, the mass plus the bullet mass, and then mr square to the distance from the joint pivot points. The distance will be 0.6 plus the 0.15, which is L plus the 0.95 square. Okay, this timber block. This is a rotation initial. And the second part of the law, this law notation initial, we know before is pivot points here should be simple. You get 1/3 of ml. M1 is this mass. 1/3 M1 L square, because your pivot points here. So this we already proved it before, the last question. Okay. So this rotation initial and plus this rotation initial, this rotation itself is center of gravity, and plus this distance. Also, you can do this way. This rotation initial equal to center of gravity rotation initial, which is 1/12 ml square. Okay, and plus m1 and the half distance, the center of gravity to this rotation center distance, half of L, half of L square, which is 1/4. 1/4 is 3 divided by 12. 3 divided by 12 plus the 1 divided by 12 is center of gravity. 1 divided by 12 is 4 divided by 12, which is 1/3. That's why this 1/3 m1 L square. Okay, so after you get this total, after impact, the total rotation inertia times omega should be equal. This is a angular momentum, should be equal to linear momentum. And we multiply this arm from this point, the arm, which is point L plus half of 0.3. Okay, equal to point like that. And from this equation, and you can very simple solve this theta dot. Okay, this solve theta dot. You can cancel even can cancel the m, and put this one, this is a numeric, and divide by over, and then you put your number inside. This 1.1 the kilogram. Okay, we lost this 300, and this is 0.75. Okay, and this 1/3 m1 is 2.5, the low mass, and L is 0.6 length. Okay, 0.6 length square. 1 over, and this 5 block plus the bullets 0.1, 5.1, and inside is L square, because L equal to B equal 2 times 0.3 square, and this 0.1 multiply inside is 0.6 plus 0.15 square, which is 0.75 square. And then we calculate this one. Have a look, check the results. So equal to 0.1 by 300 by 0.175. Okay, divide by brackets. Dominant bracket is 2.5 by 0.6 divided by 3, and then multiply 5.1 and 2 times 0.3 and divide by 12, and the plus 5.1 5 and 75. Okay, now and then in brackets for the dominates equals 6.933. Am I right? Yeah, 6.933. This is your omega. So what's the answer? 6.9. Yeah, we get the answer. Close decimal difference. Then we move to question 5. What is question 5? Question 5 is the car. Okay. Before we go there, I have the 10 minutes break. Okay, sorry, 10 minutes break.
Some citizens on their find a safe center. Journey up sentinel unseen. But their sanctuary act snare. Night and mask. Boys and arm. Come away. Animal. Thousands of tiny polyps waiting outstretched. A feather stone. A million microscopic bullets under their outstretched arms. The weaponry, a sinister traps, sieves, harpoon, clutching tentacles. Sentinels. The same. And night after night, this random microscopic rain. End in tiny but titanic struggles. Despite huge losses, some larvae survive their perilous voyage and settle. They grow to become solid citizens, joining the clouds, waging space wars with each other. This endless lottery of settlement, life, visual tapestry, species, color, pattern, and form. The beauty and harmony is a mask. It hides chaos and competition. Reef society is shaped in the water of relentless conflict. The reef thrives in adversity, prospering despite its internal struggles. But reefs have also endured struggles of planetary dimension over enormous geological time. Through the millennia, continents drift, climates change, sea levels rise and fall. As the world moves around them, coral reefs remain, as always, immobile. They seem at the mercy of geology. Yet today's reefs have somehow survived 214 million years of global upheaval. Coral reefs rim continental shelves and cap volcanic seamounts throughout tropical oceans. But once, reefs lived in an ancient sea called the Tethys. It lay between two supercontinents and split apart, causing Africa and India to drift northwards. The broad Tethys Sea, evolutionary home of modern reef animals, squeezed out of existence. Over millions of years, it became a war zone of continental collision, earthquakes, and sea level change. And the animals evolving here came under siege. Amidst these shunting continents, brief life had two choices: extinction or escape. Today's reefs are built by immobile creatures that somehow dispersed and evolved from their ancestral communities in the Thames. But to escape the ravages of geology, they had to play an evolutionary ace. This ace not only allowed them to grow, but to change. It was sex. And every summer, the age-old ritual unfolds. Shoals of tiny fry appear, their parents, the spiny crows. Their behavior is unusual among reef fish. They guard their growing offspring. A female cuttlefish holds an egg daintily in her tentacles. She chooses a nest with great care and places the fertile egg securely within. But despite her plump maternalism, this is the extent of her parenting. From the time the egg is placed in its coral cradle, the young cuttlefish will be on its own. This careful handling of individual eggs requires more time and effort than most other reef dwellers invest. The giant clam makes no attempt to nurture its young. However, it does invest enormous energy producing and broadcasting many millions of eggs and sperm. With each mighty attraction, the waters of the lagoon turn milky. Fish dart closer, feasting on the seasonal delicacy. Other, perhaps more prudent species will wait for dusk before they begin to swarm. The male coral trout emerges in sober courting colors. With his tail flagged black, he patrols his territory. Females are lying low on the beach, their swollen bellies heavy with eggs. Concealed in the watery twilight, they await the male's advances. His elaborate dance is designed to tempt the female from her retreat.
Okay, we consume our the workshop. So this question is about the car hit the lights, the side of light stand. Okay, is this light stand designed break away from the base? Okay, I assume that they break away from the B point, break away. Okay, and then with the negligible resistance from the video taken of the collision, it is seen that post was given a angular velocity. Give the after impact angular velocity already know omega equal to 60 omega radial per second. When AC is vertical, the post have a mass of 175. Okay, post a mass of 175 kilogram at the center of gravity this point. Okay, this is the mass, we know that. And also radius of duration about the axis, duration about axis perpendicular to the plane of the polar assembly past the G, which is along this point. And the radius of duration will be k equal to 2.25. So if you know mass times kg square equal to rotation initial. Okay, And rotation initial multiplied I omega, that's your momentum. Okay, this momentum, you start from begin before your impact is 0, and divided I omega momentum, and they should be equal to impulse, which is your strike force multiplied the time, right? And because it's I omega, you have to strike moment multiply time. So m delta t should be equal to I omega. That's how you get it. Okay, and then you can decide for this equation. You can decide what is decide the horizontal impulse, and which the car apply for the post. While AAC is assembly is vertical. Okay, that's already found out. So you have a m I omega. I omega already know that should be equal to impulse, which is your moment, just impulse multiplied. But this is impulse this point, right? So impulse this point, and then it broken here. There should be rotation along this point. So this distance 4 minus 0.5 is 375. 375 multiplied f delta t equal to angular what's called the angular impulse equal to I omegas. Okay, and then from there you can find out what is impulse at point B. Okay, so how can we solve it? Can come up, and that's 11. So and if the lines f delta t, this impulse multiply this distance, because this rotation center is g, so 4 minus 0.5. Okay, this is a angular momentum. This angular momentum equal to Ig omega. Ig equal to mk square omega. So you divide by 3.5, 4 minus 3.5, and then you should be able to impulse momentum equal to 150,187.5 Newton meter straight away. Okay, this will be straight away. However, if this light stands, the fall along the base is not blocking here, fall along the base. So, and without blocking away. So it means this whole line spot will follow that the pivot point will be A, if that what happened. So there you have impulse F delta T multiply the rotation center, which is A, this distance, which is 0.5. They're equal to I, and then whole rotation along the A. So IA omega. So IA rotation initial IA should be equal to central gravity ratio IG. IG is mkg square, and multiply the distance from G to A, which is 4. Okay, so equal to RA equal to the mg and the mr square. mr square, this distance, so equal to r square here, and multiply G. Right, so RA equal to 2 part. One is in the central gravity rotation initial. Okay, equals to mkg square. Another one is mass multiply distance from here to rotation center A, distance 4. That's why you get 4. This r squared 4. Okay, 4 is 16. That's why you get this one. And this m is 165. Omega is 60 divided by this is distance 0.5, and they get total is 312.5 Newton and impulse. And this impulse is much larger than this impulse. Okay, this larger because you have to, if you falling down at the base. Okay, not broken down. If broken down, the impulse is much less. If falling down, the whole thing falling down, you need a very large impulse for that to do that. Okay, that's for this question. And this is question 5. So with summary, so it depends on where you broken down. You broken down here, rotation, where's the rotation center? Okay, rotation center, you use the impulse times distance, get angular momentum, angular impulse. Okay, angular impulse. angular impulse should be equal to I omega. I should be rotation initial here, mk squared multiply the omega. Okay, that's all. If, however, if you broken, it's not broken here, broken here, then you should be this impulse multiply this distance, the angular momentum. Okay, so for the angular impulse, so angular impulse should be equal to I, then this I is IA. IA should be equal to central gravity IA plus mr squared and times omega, and then you should be able to get the different impulse. Okay, that's the summary for this question. Okay, but so far we finished 11, right? This is 11, and so far we finished all the examples. Then rest of the time we will do some study the central force moments. We study central force moment. Hold on. Central force moments. Okay, so this one you go to the central force movement. You have to go to your textbook. This is engine, so textbook. So textbook will be, yeah, textbook. So textbook, you go to textbook, which page? 155 textbook. Oh, it's actually it's more than, it's less than 155. Look, so you go to 155. It's not 155 here. From here, 155 here. So this central force motion and space mechanics we study here. So from this we study this page. Okay, 155. Okay, we study how develop these kinds of the satellites and Earth, how develop this E. I just tell you how to do that. So with definition is if the particle is moving under influence of a force having a line of action which is always point to the fixed point, O, and the motion is called the central force motion. The type of motion is common caused by the electrostatic or gravitation force. For example, this is this satellite, this is Earth, or this is the planet, this is Sun, or this is kinds of electronics. Okay, or this kinds of it's kind of one electronic, another electronics, maybe like this kind of thing. Okay, and we start typically this issue. In order to analyze the motion, we consider particle P. Particle P, this particle P is here. This particle P motion, and the force, you have the central force. We have that central force, and we assume this is we have used the polar coordinate. Is point out is r is positive, and this theta is anti-clockwise. It's positive. Okay, and this is our coordinates. Okay, then we have we study this coordinate in figure A. Okay, so they which have a mass m and acting on upon only by the central force point to the central O, which is if this is positive, is negative f. Free body diagram for the particle is shown in the figure B, which is this is a force, only one force. Okay, and use the polar coordinates r, this positive theta, this is anti-clockwise r theta, and the equation of the motion sigma fr equal to 0, sigma f theta, sigma fr equal to ma ar, sigma f theta equal to ma theta. Okay, this is Newton law, the law of motions, Newton law. Okay, for Newton law, we get sigma fr equal to ma r, sigma f theta equal to ma theta. Okay, mr is what? Mr is this direct acceleration. There should be two parts. One is if r can be extended, move in this direction. So dr differential two times, get the acceleration this direction. And also because this r, you have theta, have moved theta, tangential theta. So tangential theta, you have r omega square. You have a centripetal force acceleration, which is centripetal acceleration. and m times centripetal acceleration equal to centrifugal force. So you get the centrifugal force. Okay, so equal to the total acceleration equal to dr differential 2 times r dot dot, and minus, because there's centripetal acceleration is point to the all directions. Oh, it's negative, so negative r omega square. And this is total acceleration. M total acceleration equal to sigma f. F is to this direction is opposite the positive direction, so minus f. Let's get this equation first. And then for the tangential direction, theta direction force, f theta equal theta. You have a theta direction, you have no force. So this force equal to 0. And the acceleration, what's happened? Acceleration equal to m. You have a theta, you have a d theta dot dot r theta. This is tangential acceleration in the tangential theta dot dot r is tangential acceleration. Okay, and plus 2 omega cross multiplied r dot. What this means? This means you have this is anti-clockwise. Anti-clockwise will be, you have looked this you have this anti-clockwise from here to here. Use hand. I just show you. Hold on. We just show you the. Hopefully, we can show you the screen. Hold on. Hopefully, it works. Look. So from, if you see my hand here, they should be like that, because and from the anti-clockwise should be like that. This point up, okay? And then you have another r direction is point out. So from the up to the out, make a right hand rule. Then this direction will be point tangential direction to the theta moving direction. And that's you get. I can go back again. So we go back here, then we get so you have a omega. So omega is point up, and r dot is point out. So you have right hand side rule. You can, this direction will be point to the tangential direction, should be point to this direction. So after you get the direction, you get rid of this kinds of vector, become d omega is d theta dt, r dot is d theta dr, but this r will not change in the radius, so this is equal to 0. Don't worry too much. It's mr theta dot dot. So in summary, we look at the second equation. Second equation, you can get equivalent to this one, equal to this y. You can make, if you don't believe this is equal to 0, go get out. This is 2r d theta dt d dr dt. This one, and the plus r square and d theta dt again. The second theta, okay, and this r be cancel another r. So that's why you get this one equivalent to this one, equal to 0. This one equivalent to this one, equal to 0. And from this one, integration 1 times, this one should be equal to constants h. This is integration constant, depends on initial condition. Get this one, okay. After get this one, and then you get d theta dt equal to h divided by r square. That's what you get. R is the integration constant. That's equation 1 you get. Okay. And then you find the first equation, this equation. What happened? This equation, first equation, we let r equal to 1 divided by cos c. All right. So then we can get dr dt equal 1 over cos c squared d cos c dt, right? And then we replace the d theta by d dt, replaced by d theta. Cancel that, replace by d theta, because they cancel. All right. And then from there, we have dr d theta equal to, you multiply d theta divided by d theta equal to that. And then d theta dt equal to h divided by r square equal to like that. So this one, keep this. This is h divided by r square. So then we get dr dt should be equal to dr d theta r, all right, h r square and h r square, and then this d theta d theta dr equal to this one. Replace this one here, and then you get this one. Okay, because here dr d theta equal to this one, multiply this one, but dr d theta equal to this one, put here, and then you get this one. Okay, and get this one, and you know r times this one cancel. Okay, that's why you get minus h d c d cos c d theta. Okay, and then differential another time dr d square, and differential another time this one differential equal to h d theta d this one, and then multiply d theta divided by d theta, you get this one, and this d theta dt equal to h divided by r square, and multiply r equal to h divided by r bracket square, and this rest of dr d theta d cos d theta. Okay, after that, and then you have what? You have this one is a h square outside, and the r square is cos c. 1 of r square equal to cos c square, because r equal to 1 over cos c. So then with another h put inside the same thing. Okay, so that's why h plus h square. Okay, this 1 over r square become cos c square. After I get the equation 4, and you arrange equal to cos h d theta dh. That's done equation 5. Okay, from equation 1 to 5, we know minus f equal to dr dt square minus r d theta dt square, and you replace this one put here, this one put here, and then minus you get this, replace all this one by this one, and you get this equation. After you get this equation, and then you divide by, because you get divided by h square, because h square divided by h over h square, and this one d theta dt equal to h r square bracket square, which is h square r fourth, and cancel the r, become r third h square divided by over, and then h third r third equal to, and r square multiply r. Okay, r square 1 over r square equal to cos c square, and divide by cos c square. This cos square is gone. This is h is gone. So this one divide only have d cos d theta square, and this one only left 1 divided by r. All right, 1 divided by r. 1 divided by r is cos c. That's why you get this one. Right. This one you make this one left hand side, this one right hand side. Then you final result you get this one. And we know this force for this kind of a central force, if it's for the gravity force law, if for Earth a satellite, this force should be equal to this one, this Newton gravity law, equal to constant of gravity constant, multiply the Earth's mass plus satellite mass divided by distance between the center of Earth to the distance of center of satellites. This is the gravity, law of gravity of Newton. Okay, Newton proposed this law, and put this one inside this equation, and r, and the r square become r square multiply cos c square, cancel equal to 1. Then this equation becomes this equation. This is constant. This constant is easy, because for this one, for this equation solution equal to homogeneous equation equal to 0, general equation, which is c cosine theta minus 5, plus special solution, which is cos c equal to this one, special solution, because differential total equal to 0. This one equal to 0. This is special solution plus general solution. So for the homogeneous equation, general solution plus the no homogeneous equation, special solution, you get this solved differential equation. Okay, and then you get this one. This is your solution. This solution is cos c solution. Cos c equal to 1 over r. Okay, then finally you get your equation will be like that. And you study, if you, this is a flight trajectory of satellites. Okay, you study is if you study this at the beginning, r cos c equal to 0. So you study your this position, if this theta angle equal 0, r equal to r0. So this one, then you get this equal 0, cosine 0 equal to 1, and this r0. And then you get c equal to r over r0 minus this constant. You get the c here. And then you replace this c into here. And then you get the final equation. That's your, this is Earth and satellite equation. You use this equation. Okay, this equation. And then you organize that, make a r1 r0, and you organize that, you will get this one. All right. And usually you can make simplify it. Put this is the 0 position and make this one, get rid of theta, make theta phi equals 0, make simplify. So that's why. And also from physical meaning, this this defined is F for the astronomy is a PF divided by PA. This for E, okay, for E. And then this F for FP equal to FP should be equal to E multiplied the PA. So what is PA? PA is this one. PA is this one equal to how much? Equal to P. P minus this distance. This distance equal to R cosine theta minus phi. Cosine theta minus phi. Okay? And then you get R equal to E and the P minus equal, take this R, this part out. And both sides divided by EP and R divided by here. And then you get R, 1 of R, this cancel, 1 of P cosine. And this divided over 1 over EP. You get this equation. So from this equation, and then you remove R, 1 of R equal to this one plus this one move to left hand side. So 1 of R equal to this one plus 1 of EP. So you compare this equation with equation 9. These two equations, this equation you can simplify what C equal to 1 over P. And the 1 over EP should be equal to this one. 1 of EP should equal to this one. Okay. So by comparing these two equations, then you get C equal to 1 over P. And then 1 of EP equal to this one. Then you get because 1 of EP, this is C, right? Get the C. Then you get the E. So this 1 of P equal to C, this is C. And you solve the E equal to this one, get this one, right? And you know C before, we know the C is equal to C we solved before, with C equal to this one. Put this C into here, okay? And then you get finally the E formula, okay? Well, finally you get the E formula. E formula should be equal to formula, okay? And then we assume that origin position and phi equal to 0 and h equal to h0. So d theta dt equal to h divided by r0 because the initial position is theta equals 0 is a initial condition. So this one, initial theta equals 0 is r0. That's why you get d theta dt is equal h divided by r0 square equal to that. Oh, this is constant from the integration constant from the initial condition, okay? And then initially the velocity equal to omega times r0. And then you compare this one, you can get h equal to r0 multiplied v0. That's, you get h, okay? And this one origin is C. Replace C by this one, and then you get the final equation like that. And this C is this part. And also you can put this one into the C, and then you get the final your E equal to this one. And that's why you remember with the big last with the exercise lecture 3, and for the different E position, different position for the circular E equal to 0, use this for equal to 0, and then for the elliptical E should be less than 1, and for the parabolic E equal to 1. Okay, for the hyperbolic trajectory E larger than 1. They use this formula, you can do calculate the different R0, and this R0 and minus the radius of the Earth, you can get height. That's why we how we get this formula come from. Okay, that's why. So type of a path traveled by the satellites is determined by the eccentricity of the conic section given by this one. Okay, this is for that. All right. Then for the parabolic path, we actually know R0, V0. Okay, we know that. And parabolic path, we use the E should be equal to 1. This one equal to 1. And solve this one, you can solve what is R. You can solve the R0. Solve R0. Parabolic. And parabolic solved R0. Okay, also you can solve what is if you know R0, you can solve the parabolic what is velocity, the minimum velocity for parabolic. Yeah, otherwise less than this one, and this for parabolic is here. If less than this one, there will be I think if more than this one, this satellite will fly away, never return. If less than this one, will be second, we come back. Okay, so be careful. That's why you get this is escape speed. You can find the escape speed. And this you find the escape speed like that. So this is escape speed. You solve this, get E, and because this, hold on for here. So for the parabolic, H equal to R0, V0, and codon differentiation, this is E equal to 1. Equal to 1, you can solve the E, V0, VE. This is escape speed. Okay, you have to more than this speed. Okay, if you have the less than this speed, if more than this speed, they will not come back. You have less than this speed, otherwise they never come back. And then for circular path, E equal to 0, and then you find what is circular speed equal to 0, and then you should find what speed should be satisfied this one for the escape. Okay, so if for more than this one, there won't be the circular. Okay, it have to less. But if too little, if too small this speed, then this satellite will go back to automorphism, and there will be the ER0 represent the minimum the height for the launch, in which the friction resistance from the atmosphere is negligible. But this speed, if less, they will cause satellite to re-enter the Earth's atmosphere and then burn up or crash. And that's the important for this speed calculation critical. So it should be more than this speed. Okay, if less than speed, we go back to the Earth, these satellites. Then we go to the elliptical orbit. Elliptic orbit, you have to use the E. Again, E should be less than 1. And the less than 1, you can solve this. You have to satisfy this RA, and the elliptical, you have two. This is RA and this is RB, right? This is B and A, right? So this is the shorter distance. This shorter distance is RP. Long distance RA. Okay, this is 2B and this is 2A. This is elliptical, right? So from this calculation, if you go to for the minimum distance, the theta equals 0, we already get theta equals 0, which is R0. R0 is RP, right? For the maximum distance, will be this theta should be 180 degree. So from this equation, 180 is minus 1. From this minus 1, you can solve what is R. This RA. RA, solve this R, should be RA when cosine theta equal to minus 1, which is 180 degree. Then you get this RA, and then you reorganize the RA like that. If you know RA and the RA, if you know RP, which is R0, they sum together, RA, RP plus RA sum together, divide by 2 is A, right? That's why you get this ellipse, the A. Okay, the major axis half length is RA plus RP divided by 2. And for the, how about for the, because this is, and also we can prove this for the RA, RP, multiply square root, you get B. Multiply square root, get B, because it's an ellipse is this property. we get half length of minor axis ellipse. All right, and then for the area of elliptic area of the ellipse should be pi AB. This is why this area pi AB. You can find your high school the geometry formula manual. Okay, you can find this one, and it should be equal to A equals square roots RARP, B equal to I think A equal to RARP divided by 2, and B equal to square root RARP. Okay, and then for the area velocity dA and dA dt, you can prove dA dt should be equal to half of h, which means you have half h. You can write this way. You can have this is your A, right, and this is your time axis t. So you have a constant slope, and this should be h. This should be your t. Okay, this should be your h. So this area, okay, this integration is area. Integration is A. Integration area, it should be this h multiply the height divided by 2. That's your area. This is your area, which is A. Okay, and this area is this curve. So A, this area of ellipse area versus time, this slope is linear relationship. End of t should be h. That's why you can make h multiply t divided by 2 equal to this area. Come up from here. And this is your t, and then dA dt, you get a constant. That's why I get the constant half of h. Okay, and then from here you can solve this p area and divide by h a p area, and this is your p area. You can solve the p area for ellipse, for the satellite p area along the ellipse motion. Okay, and then the theory developed in this section is applicable to predict the actual motion of the planet. This theory is we use the Newton the law of motion, second law of motion, to establish this different trajectory and the motion for the satellites motion along the Earth, right? But this theory can be also applied for to predict the actual motion of the planets travel along the sun. They use the same formula, the same law. In this case, m is the planets instead of mass of Earth. Okay, so it's one mass of the Earth satellite. M is planets instead of mass of Earth satellites. ME, before we derivation Earth's mass, but in this case, if you move to planet motion along the sun, then this ME becomes the sun mass. Okay, should be replaced by the sun mass in above formula. So this law can be transformable, or can apply for the planar motion travel along the sun, because this developed from the satellites travel along the Earth. But this one same formula can be applied to predict motion of the planet along the sun. Okay, the only change is m. Then before it's satellite, now becomes the mass of the planets, and the ME before it's Earth, now is the mass of sun. The only difference. Okay, the fact that planets do indeed follow the elliptical elliptical orbits along the sun was discovered by German astronomer Johannes Kepler in early 17th century. Okay, his discovery was made before Newton has discovered the law of motion and the law of gravitation. Remember, our derivation, all this formula is come from this one. Remember, derivation come from the very earlier time. We come from this one. This Newton. This is Newton Newton law of gravitation. Gravitation law. This Newton discovery based on this formula, and also based on this one. Based on this one, this is Newton motion, the law of motion. F equal ma, second law. Okay, all this derivative based on Newton law. This one and and this one. Okay, but this get the conclusion. For this conclusion, he get from this conclusion, and this conclusion is this conclusion actually he observed the Kepler observed the following okay, this one, his discovery, this kind of is far before Newton developed the law of motion and the law of the gravitation. So at the time, it provided important proof as validation of this law. He just validates the Newton law. What kind of observation he observed? Kepler's law developed after 20 years of the planetary observation. What his observation? The orbits of each the planets is ellipse with the sun placed at one of the focus, and that's one here. That's why replace Earth by sun, replace Earth by sun, and this replace the satellite by the planets. Okay, that's the first observation, and also to follow this ellipse, track is ellipse, and this Kepler observation. Kepler observation not based on this mathematical derivation, based on independent the astronomy the observation. Okay, so he get the first observation like that. This observation already proved by our equation, right? Second one, square of the period any planet is directly proportional to the cubic of the major axis of orbits, which is this formula. You get the t square. Remember t square. This one pretty much cancel. This one pretty much is second order. This is first order. Multiply third order square roots. Third order square roots and t square, get rid of square root, become t cubic. That's why proportion t square proportional cubic of this axle. And that's the proof that this is observed by the Kepler. This is proof that Newton law, because this is derived by Newton law. This one developed the Newton law. This was derived by Newton law. Proof the Newton law. Okay. The third one is every planet travel in its orbit, such that the line joined it to the center of the sun or sweep over the equal area in equal interval of time, whatever the length. What this means? This means is this formula: d a d theta in individual equal time in sweep the area is constant. D equal to h divided by 2, which is he just used this if you this curve, it's like that. I'll show you. So here you get one instance here swap. This is one. Get another in same time instant. This area equal to this area equal to constant equal to half divided by 2. That's the observation by the Kepler. And this Kepler exactly gets from derivation based on Newton law, Newton law, gravity law, and also second law, Newton's second law. Exactly. That's why Kepler observation prove Newton law, and active as proving a validation of Newton law. Okay, that's it. This for the this central force motion analysis and space mechanics, which we have to introduce. If details interesting, you are read this textbook page 155. Okay, and this one I deliver what is E, help you understand what is E, and use the E. You can do that exercises. If travel in the, you know the E formula, and the E formula is like that. If you travel in the cycle, E equal to 0. Okay, if travel in the parabolic, E equal to 1. If travel in the elliptical trajectory, is E less than 1. If travel is hyperbolic trajectory, E larger than 1. That's why I just get how this E come from. That's the purpose of teaching you about that. And also I teach you how this delivered by Newton's second law. This conclusion is and before this Newton law, Kepler already observed this from 20 years planet observation. This conclusion proved that Newton's second law. That's how we do that. Okay. Then the last one, we move to the engine, IC engine. So IC engine, first we go to IC engine. IC engine power have two kinds of power. One is indicator power. One is brake power. Okay, indicator power is measured from cylinder pressure. Brake power is measured from at the crankshaft. You measure torque, multiply the rotation speeds, and then go brake power. Okay, brake power is always less than indicator power. The reason is because of the engine have a reciprocating piston connecting node, a crank angle, crankshaft. It's have a friction, and also have intact exhaust type of valve pumping noise, throttling loss, pumping noise. That's because this friction, a pumping loss, they make output shaft torque is always less than the gas pressure. Already gas pressure creates the power, which is called indicator power. Okay, so how can we get this formula? So indicator power should be equal to mean effective pressure of cylinder pressure. This will be calculated for the indicator diagram. Measure the pressure transducer, get the indicator diagram of engine. You calculate mean effective pressure. Multiply L is stroke, length of stroke, and A is piston area. Okay, N is RPM, rotation speeds, and this small n is if how many cylinder, number of cylinder, and they also be careful. There's miss something because this is a revolution per minute. In order to become the radio, have to multiply 2 pi. Don't forget 2 pi. And also K depends on if you have a 2-stroke engine, K equal to 1. If it's 4-stroke engine, K equal to 1/2. Okay, that's important because for the 4-stroke engine, 2 revolution, 1 firing. That's why you have to multiply half. And on 2-stroke engine, 1 revolution, 1 firing. That's why K equal to 1 for 2-stroke engine. Or for brake power, develop power equal to torque multiply the omega. Okay, but this is standard SI units. It's Newton, this is radian per second. But in real life, we have to use RPM, revolution per minutes. Revolution, in 1 revolution, 2 pi. Okay, 2 pi is radio, right? And per minute is 60 seconds. That's why use the n 2 pi n divided by 60. You change in the RPM equal to radian per second. Why divide to 1,000? Because this SI unit equal watts, and you want to kilowatts. That's why I divide 1,000. That's why you get the brake power equal 2 pi Tn divided by 60,000. That's what this for the brake power as well. Okay, the same thing. The Y, because this RPM, the Y I said and this the engine RPM. Revolution per minutes. That's why you have to multiply 2 pi divided by 60. The same principle is the same. And they want to get the kilowatts, you have to divide by 1,000. The reason is the same. Okay. And then we go to 4-stroke engine, how it works. Have a look. The first of all, intake, suck the air through the intake valve, go to a suction stroke. This is called intake stroke. Suck the air inside. Okay. After that, reach the bottom center, start move up, and this one intake valve close, and the exhaust valve close, and the compress. This go intake stroke, and then this compression stroke. Compression stroke. They should say that. Induction stroke, compression stroke. After this, piston go to top the center, and then have a mixture ignition. Spark plug ignition. Ignition make combustion. Combustion will push this piston go down. This go power stroke. After reach the power stroke, go to both the center, and then the piston move up. And in this time, the exhaust valve open, push this exhaust gas go out. It's called exhaust stroke. So you have a induction stroke, compression stroke, expansion stroke, power stroke, and also is an exhaust stroke. The 4-stroke engine. Okay. What happened for the 2-stroke engine? How it works? We can look at the 2-stroke engine. Two-stroke engine, we start from the power stroke. With the top of the center, they have a compression, the fuel and the gas mixture and the ignition. Push this piston go down, and then move down. This is called power stroke. Okay. After power stroke, moved in some position. This open, move down further. This position. This is the open is exposure, and then originally inside have some air inside this cylinder. This air will have pressure pushed down. This pressure will push this air inside the combustion chamber, and this air will sweep because they will push this kinds of unburned gas. We push it out, exhaust gas out, and push this some air and the fuel push in. The sweep from in fresh one and push the exhaust out. This is called this is called exhaust stroke. Okay, stroke structure. This is called transfer. Transfer from fresh air, push the exhaust out. Transfer stroke. Okay. After that, and then you should go further down, bot the center, and then push up, and then push up. You above this two position, and you close these two ports. Close two ports and make a compression. Increase the pressure, compress this air and fuel, and then go further down, go to near the top of the center, go to further down, and then you exposure this come in, and then you find this air will be taken in. But take in, they will not go to combustion. We go to this cylinder body, put all air inside. Okay, put the air inside, and after that, go further up, and get the minimal the space, and then then you have the injection. Then you have the ignition again, and then they do actually before your ignition there should be use fuel injection fuel. Okay, injection fuel and the ignition and come back again, power stroke again, push again, in that cycle come down. The difference is this two-stroke engine, they combine intact exhaust together. Okay, and also there will be sucked air, not direct sucked into the combustion chamber, sucked in the cylinder body. Okay, and the cylinder body, and then sucked in, store here, and when reach this position, they push this push this air into the combustion chamber, and they push this exhaust out. That's combine this intact stroke and also exhaust stroke into one. That's why you get a two-stroke. Advantage for the two-stroke engine is lighter and also simple, less expensive to manufacture, and also have potential to produce twice power, use the same space compared with the four-stroke engine. Why? Because two-stroke engine, one revolution, one ignition. Okay, and then four-stroke engine, two revolution, one power stroke. So one revolution, four-stroke engine only have half of power stroke. That's why you say that potentially two-stroke engine have a double of the power output compared with the four-stroke engine. And this combination gives the two-stroke engine great power to the weight ratio. This is the advantage in two-stroke engine is shorter because combustion ratio be lower. So the life is much shorter due to lack of proper lubrication system, and bearing and spark plug worn out very quickly. Okay, and they produce pollution because they burn. They relied on the mix up the petrol with the engine oil together, and this one will provide the lubrication. That's why this one will provide the pollution. So if you have some trimmer two-stroke engine, you will see you have used the petrol mix up with the oil together, filled into and make combustion. So when they do combustion, they get some kind of oil into to lubricate, because they mix up petrol and the engine oil, they make the pollution be higher, produce pollution. And because combustion ratio is not very high, so fuel efficiency is low. And also lubrication oil for engine is expensive. That's why you put fuel price expensive. That's a disadvantage for the two-stroke engine. And then we can see the two-stroke engine, how they works. And this formula we already said before, we're not going to repeat. We already mentioned before the first slide. The difference, you can see that there is a transfer port here, which is your original intact go to this body, this crank box intact, and then in some position they will push this one, open this one, push this air will be go into the combustion and push the exhaust out. That's combine the intact and exhaust together. That's why it's called two-stroke engine. Okay, and then how's the configuration of the engine, four-stroke and two-stroke engine? Can look. So this is object. I will look at another one. So this will be flywheel. Flywheel to smooth out fluctuation for the output torque. And this crankshaft, and this one is crank balance mass. And also this crankshaft knots. Okay, this main bearing Juno bearing here. And this crank pin bearing, crank pin oil passenger. Okay, crank pin oil passenger. And this is connecting node and this piston. Four-cylinder engine. See that four-cylinder engine. So if the two revolutions, 4 pi, okay, 360 multiplied by 2, 720, 4 pi. 4 pi, if you have only one cylinder, finally the output the torque, one peak come up. So not even. So not very nice. But if you have a four-cylinder engine, they have 4 pi, they have a 4 peak come out. So more evenly. Okay, and then from this one you can find the average output mean torque. And this torque should be equal to the engine dynamometer friction torque, should be balanced. Okay, and then you can keep the engine with constant speed. Otherwise, the engine will not be constant speed. So this is a piston. This is connecting node. Usually you have to lump this whole connecting node. The mass equivalent to 2 lump mass, this end and this end. And this is a crank also have a lump the whole mass into this end and this end. So you have the mass here, and you have mass here, your rotation to have a centrifugal force. In order to cancel the centrifugal force, you put another mass here to cancel this centrifugal force, make a balance. That's called engine balance. That's why you get the engine balance mass here. Engine balance mass. Cancel the centrifugal force. Okay, cancel the centrifugal force. And also from the combustion torque and minus this kind of dynamical friction torque, and this output torque, this is your output torque, this area output torque. Energy is this torque integration over this 30 theta, this energy output, see that? And ideally, this one, T theta, and should be balanced by the average PC, the factory average should be balanced by TL, ideally. Otherwise, the speed will be accelerated, will not keep constants. There's the four-stroke, power stroke, exhaust stroke, intact compression stroke. Power stroke, you have a gas force very large. Rest of the stroke, you have the initial force, reciprocating initial force creates a force here. So only have a power stroke and compression stroke. This gas pressure will be add on that. Okay, so you sum together gas force and the reciprocating initial force, and then you calculate the output torque should be like that. This is your combustion output torque and have fluctuation. Okay, this is positive, negative, positive, negative. The fluctuation always has mean value. This mean value should be equal to the engine dynamometer provide the friction torque, and then they keep the engine speeds will be stable. Otherwise, engine speed will be increased, accelerates. Okay, that's how it works. And this one make more and depends on if you use this is the torque fluctuation, total torque fluctuation. Average should be balanced by the engine dynamometer friction torque. But if you have a big flywheel and this fluctuation can be reduced, why? We can talk the reason. Okay, so T output torque equal to rotation initial times angular acceleration. We know that angular acceleration equal d omega dt. You multiply d theta, divide by d theta. Okay, and then d omega d theta here and d theta dt. This is your omega. And this one, d theta move over, t d theta integration from one period equal to energy, right? Output energy or work should be equal to I omega integration, and your your NGRP omega equal to minimum to maximum. So there should be integrations half omega square equal to omega maximum square minus minimum square. Goes from minimum to maximum. And here you can multiply plus and minus multiply together. Plus divided by 2 is average omega. And this is the range from minimum to maximum, fluctuation range. Okay, we define this called fluctuation factor. Fluctuation factor is the range multiplied average omega, average rotation speed. Okay, this is called fluctuation factor. So put the inside this one, k times omega average replace the omega maximum minus minimum, because maximum minus is equal to k multiply omega average. And this is another omega average equal to I omega average square times k. All right. So in order to, then you get I optimized rotation initial equal to work or energy divided by k and divided by omega average square. We assume our average square is specified. So in order to reduce the, you have to reduce the fluctuation. Fluctuation, you have to reduce fluctuation. You have to increase the rotation initial, which increase the flywheel. That's how you get this formula. Okay, this is constant. This is constant. Reduce fluctuation, you have to increase the rotation initial. That's how you design the flywheel. Give an example. So determine the requires the momentum initial of a flywheel for the single cylinder engine at the speed of 3,300 RPM. This average rotation speed. And the maximum allowable fluctuation in speeds will be 40 RPM. This is fluctuation range 40, maximum minus minimum 40 RPM. Okay. The work of torque is 463.7 joule. And then you get the I, the formula, this energy divided by k divided by omega square. And this k, you can calculate 40, which is a range omega maximum minimum divided the average the omega equal to 0.02, right? You get that. And this one is 3,300. You become SI units. You can calculate omega SI units equal to this one. So you put this one together, and you do the work together, and you calculate I. This flywheel rotation equal to U, which is energy, which giving energy 400 is 463. Give 463. 463. This is U, okay? And then you divide by K. K, we know that's K, we already calculate K. K equal to fluctuation range 40 divided by average speed equal to 0.014. And divided by average the omega, average rotation speed is SI unit is 346. Is RPM is 3,300. And this square. And you calculate this one, and the end result equal to 0.321. So in order to achieve this fluctuation the factor, okay, and also at this speed you need the flywheel about 0.321 flywheel. At least you need this larger rotation initial. Okay, that's all for the lecture. Time is up. Thank you very much. And if you have a further question, you can contact me by email. Okay. Hold on. So second. What you said? Go to. Hold on. What's that? So will space mechanical IC engine be in exams? I don't think so. Don't worry. This is only for your interesting. And tips of exams. Just go through the video recording. Try to understand each week the question and solution. If you know exactly how to do it, you will no trouble for exams. Exams only change the number, okay? We're not exactly same as example, but we'll change a little bit number. You'll be fine if you understand how to do it. Okay, any other question for me? If not, then good luck for your exams. Good luck. Multi-choice. I don't think it's a multi-choice. They give you in multi-choice form, but you have to write your answer and upload this your answer by either by PDF file or by the JPG file. Take a photo to do that. How many questions? I think You have 3 hours, so you have to find. Maybe you should satisfy 3 hours question. You understand? You have 3 hour writing time. You have half hour reading time. So 3 hours. How many you can do? I think you at least you have 5 or 6 questions. I believe so. Yeah. Yeah. So the tips is in workshop note. Correct. Correct. How many question? A question number is maybe 5 or 6. I believe. All right. TT stress. Aha. What means TT stress? All right. No stress. Okay. Easy. If you make sure you understand each question, you understand the video, and you will be fine. No stress. All right. Any other question? Otherwise, we finish. Thank you very much. We stop the recording. Okay. Okay. No worries. See you. Good luck for exams. Good luck.